The next generation alternative proteins for food, fundamentals and technological innovation. And today, the 12th of October, we are going to have two lectures. The first one is lecture number 12. We are going to talk about chemical and enzymatic modification of plant or alternative proteins to improve techno-functional properties. Again. Start from the start, beginning. Okay. All right. Hello, good morning everyone. My name is Mahesha, Manjunatha Poojary, and welcome to the 6th day of the Gian program, Next Generation Sustainable Alternative Proteins for Food, Fundamentals and Technological Innovations. And today we are going to have two lectures, lecture number 12, Chemical and Enzymatic Modification of Alternative Proteins or Proteins in general to improve the techno-functional properties, and the last lecture will be the lecture number 13 for today, scaling up production from lab to commercial scale. So, let us begin with the first lecture. So, in the first session we are going to talk more about how do we use certain treatments to improve the techno-functional properties of proteins. Okay. All right, so let us a little bit summarize again what we have been doing yesterday, right. Yesterday we were talking more about how we can use different techniques to improve digestibility, or what do you mean by digestibility, and what do you mean by bioavailability, and what are the different techniques people use to assess the protein quality today. What do you mean by anti-nutritional factors, and what do you mean by allergenicity, and how alternative proteins can act as allergens in certain situations for certain human being, and those things we have been discussing. We talked about in vitro models, we talked about rats, we talked about piglets, right, and we discussed about why we are using DIAAS instead of PDCAS today, and what are the advantages and disadvantages. Those are the things we discussed. Any question for yesterday's topic? Unfortunately, we were running short of time and I could not have a lot of time to ask you, ask you this question. If you had any question, any doubt in yesterday's class? All good? That's fantastic. So, then let us move on with the today's lecture, and again we shall see how today's lecture syncs with our previous topics. I would like to do this exercise again. So, we had day 1. What did we discuss? Why we have to go for this transition from animal based to plant based. We discussed a lot about alternatives and why really there is a need for alternatives, alternative proteins in general, right. And that is something we discussed, and then we moved on to the day 2. What did we discuss on the day 2? Exactly. On the day 1 we discussed about how different types of alternative protein sources are available, but they are locked in the biostructures, right. It is very important to get them out, otherwise maybe they are not very functional. So, we discussed a lot about different extraction technologies, both conventional and innovative technologies, right. Then move on to day 3. What did we discuss on the day 3? Characterization technique, good. Characterization. So, how we can use different analytical tools. For example, we discussed about how do we measure primary structure, secondary structure, what do you mean by STS page, what do you mean by chromatography, and what are the advantages of using chromatography in protein characterization. And finally, we briefly went through mass spectrometry, how this fancy equipment can give you the best or the better idea of protein structure, modification and so on, right. And then we moved on to the day 4. Yes, exactly. Now we know we have proteins in hand, we have characterized them. Then what? We would like to know where it can be useful. What is the exact techno-functional properties our proteins that we have extracted possess. To that we talked a lot about functional properties. I think we discussed almost everything, I would say, but the most important ones, let us say solubility, emulsification, water holding capacity, oil holding capacity, and how these different functional properties can be analyzed using different techniques today, and what are the advantages of these techniques and what are the disadvantages of this technique, and what is most commonly used in the literature, what are the pitfalls, those things we discussed. right. But of course, I did not cover other functional properties like gelation, for example. I could not have much time on that, so those things I did not cover, but I will try to touch upon some of the aspects in the coming classes, right. So, now we understood that our protein is functional, it is binding to water, for example. Then what did we do on the day 5? Day 5. Yes, one of the things we checked was texturization, extrusion technology, and that was something we discussed about. Okay, now we have a protein with very high water binding capacity. Let's say, can we make it as a meat analog, right? Then we discussed about shear cell technology. We discussed a lot about high moisture extrusion technology. But there was also another lesson on that morning. Exactly, exactly. So I think this one was covered here. Yes, right? With the covered, yes. On the day 6, day 5, that was yesterday. Now see, I'm lost kind of. So that's why I'm doing this exercise. Day 5, we discussed about, on the day 5th, we also discussed about functionality and also improve the functionality using high moisture extrusion. And yesterday we discussed more about, okay, now I have my food in my hand or my food ingredient in my hand. Okay, now I'm going to eat it. Okay, from mouth, what does happen now? So those things we discussed. We talked about mainly protein quality parameters, especially why quality is important in addition to quantity. So where we discussed mostly about digestibility, I just summarized it already now, and we discussed also about ANFs and anti-nutritional factors and allergens, right? And we briefly discussed, okay, how we can use germination, soaking and other things to, or heating to inactivate all unwanted things, right? And this was our history, the last 5 days, you tolerated me, right? That's not the end. So the GAN program is still continuing. So we are now on day number 6. As I mentioned, there's a lot of things we have been doing here, but still there is problem, right? Every time I was telling, there is no protein that possesses everything that you need, right? It might be it having a very good water holding capacity, it is juicy now, but it might not be having a good gelation properties. It might not be very digestible, right? It might come up with some anti-nutritional factors. So every single protein comes up with its own problems. Then we want to get the best. Every time the human beings always we think that, okay, let's improve it, let's improve it, let's improve it. So one of the improvement techniques, especially in this case proteins, is modification, right? Protein has an inherent structure, okay. Please note that alternative proteins, let's say plant proteins, they are in fact, they are not built for human beings. Do you agree with me? Plant proteins are built for plants, right? Insect proteins are built for insects for their living or livelihood, right? It's not built for human being. Of course, we humans want to consume everything. That's another story. We have to do that to survive because we can't do photosynthesis, unfortunately. So, right? If we can do, maybe we can produce our own food. Now, the plant proteins are built for plants means they have a typical structure, typical composition that is maybe useful for plants, may not be useful for food, for human beings as food. So, there is a small things we have to do. Now, it was in plant, imagine, now I want to have it on the plate, right. We tried so many things, but still we need to do modification so that maybe it becomes more edible, more digestible, maybe it is having less unwanted properties. And there we talk about different chemical properties, different chemical and physical modification. And just to go a little bit further here, that food is never a one type of matrix, right. Just to give a generic idea here, sometimes we need a food that is colloidal, let's say milk, right, it should be watery. Sometimes we need milk that is kind of a soft and like let's say yogurt. Sometimes we need food which is little bit soft but little bit hard, let's say chicken breast, right. Sometimes we need foaming properties just to have it on your upper lip, I don't know. So we need something, right. And sometimes we need really hard thing just to chew, so to feel it, to feel happy. So we need food in a different ways, but that all properties does not come with one plant proteins, let's say. we need to change so that it becomes a better forming protein with a better forming properties, for example. And I also refresh this again and again. I'll bring this picture on your head just to show that all the functional properties are related to structure of the protein. Structure is very important. Structure determines how protein binds to water. Structure determines how protein interacts with another components to improve the functional properties. So, structure is important. We talked about again 4 different levels of protein structure: primary, secondary, tertiary and quaternary. All of them are important building the food structure, right. Food structure is maybe because of protein. Of course, carbohydrates and other things also play a role. Protein has a lot of role in developing food structure. Structure also determines texture. Texture is very important, right. Just to give this baking background. But we have been also discussing a lot about, okay, we can do many things, but they all come up with their own challenges. Just to summarize challenges, just to give a background for my next topic, we all knew that plant proteins or insect proteins, they might have a very high concentration of some of the amino acid, but not all. Lysines are low, tryptopans are low, methionines are low, depending on type of proteins, right, except. And then taste, they bring it some grassy flavor. Sometimes plant proteins are bitter, sometimes plant proteins what we call astringent. So, these are the problems. And then these are the things we need to look after just to improve the techno-functional properties of alternative proteins: taste, texture, flavor and all these things. We have discussed all these things in detail. It's just to refresh your memory. What do we need today and why do we have to modify proteins? And another important thing I kept telling you when I started with alternative proteins, they are sustainable, they are beautiful, they are nice, but they are also complex, right. Compared to milk proteins, compared to meat proteins, they are highly complex. Again, plant proteins are not built for human beings in general, they were built for plants. So, they are usually globular in nature, right. Most of the plant proteins are globular, storage proteins especially globular in nature, and they have a poor solubility. But when you take, we were discussing about STS page in one of the classes, somebody was mentioning that whatever I do, I get a smear, right. So, smear is a problem. It's very complicated because we have too many different types of proteins in a plant matrix, right. They are slightly different, what we call isoforms and so on. You also have albumin, globulin, prolamines together. You know that albumin has something, a different property, prolamines have a different property, globulins have a different property. Now, if I get a plant protein isolate, it is a mixture of multiple proteins and individual protein has an individual property. Do you agree? And now I am selling it as an isolate to everybody, but my end user might be dissolving it in water. My other end user may be trying to make a yogurt out of it. My other end user trying to make an infant formula out of it, right. Everybody is working with a different application with the same initial content, but this is not an individual protein, it is a mixture now. So, in different food they start behaving differently, right, because maybe in milk application maybe water soluble globulins, albumins becomes more active, I do not know. In high salt containing food samples maybe globulins becomes more active there. So, it is actually a complex mixture. So, that predicting the properties of plant proteins or alternative proteins in a final food matrix is very complicated compared to milk or other type of proteins. Remember this word, plant proteins are not alone. They always come with their friends and family members, right. And when you have friends is another story, when you have family members another story, we start behaving differently, right. Like that plant proteins behave differently when they are associated with something else. So, that thing also you have to keep it in mind. Then again plant proteins are very complex, they have a very different thermal properties. That means you take rapeseed protein as an example, it has, I have isolated rapeseed proteins. I have 2 proteins along with that. I will have cruciferin and I will have nepin, right. Nepin has a melting point say above 100 degrees Celsius. Cruciferin has a melting point let us say 80 degrees Celsius. Now, I have a, somebody sold me rapeseed protein isolate, okay. somebody sold me rapeseed protein isolate, I have napin and I have cruciferin in it. Napin melts at 100 degrees Celsius or above 100 degrees Celsius, cruciferin melts at about 80 degrees Celsius, right. Now, I was very happy, I really wanted to use it as a food ingredient, right. Then I will come, I am trying to make, let us say, a sports beverage out of it, right. I am trying to make a sports beverage out of it, I add and it becomes super soluble, I am super happy, okay. But the problem here is that we do not eat proteins as solution directly, because then FSSI will come, FDA will come, they will ask what about bacteria in it, right, is it safe to consume. Then you suddenly think, oh no, I do not drink it directly, I have to do pasteurization, right. Then you apply heat treatment. Now what do you expect in heat treatment? Okay, pasteurization I do at 70 to 80 degrees Celsius and for a long period. Then what happens is that suddenly you start seeing a precipitate, right. And the precipitate is a weird precipitate, because if you look into the melting behavior here, cruciferin melts or denatures, melting is a wrong word to use, I am sorry, denaturation is the right word. Cruciferin denatures at 80 degrees Celsius, right, around 80 degrees Celsius. So what do we see here? Precipitate mainly cruciferin, the supernatant will be napin, right. Now again I got a problem, can you see here? It was an individual protein isolate, but at the end I get a product containing phase separation. I have a supernatant differently and a precipitate, and who will drink a drink containing different phases? Do we? Phase separation is one of the challenges in food industries. We do not want to have phase separation. Now you see, the rapeseed isolate was a single powder. Nobody told me it contains so many things. I thought I want to be a plant based. Now these are the problems I will face. Now how do I get everything into solution, right? Even after pasteurization, everything should be in the liquid phase in this particular application, let us say, right. And then I have to modify the protein, does that make sense? So I do not have the problem of phase separation. Just to give a technical example how complicated this business is at the moment, right. We are right in here now, but we need to do a lot to get the real product out of it. Make sense? Here is just one example showing how the cowpea protein melting temperature is there, and that actually tells the denaturation temperature, that actually tells us a lot of information. That means, okay, if I know the denaturation temperature of a protein, now I know how stable is this protein in thermal treatment. Now I immediately understand this protein may be useful in this application, but not that application. Sometimes it is nice to denature proteins, yes. You do this heat induced denaturation to get aggregates, right, heat induced aggregates. So sometimes it is important to do, sometimes no, we do not have to get an aggregate. So this knowledge is useful. What was this figure? It is again soybean globulins. You can see that they have a different denaturation temperature, but I have a same soy protein isolate containing two different proteins, two different properties, and I might have different properties in the end product, okay. Now I also showed you this nice diagram. This was one of the nice diagrams they tried to compile, how the solubility of different plant proteins look like with respect to pH, right. One of the take home message from this diagram was, most of the plant protein, especially these globulins, right, they have pI between 4 to 6, you can see, right. They have a pI between 4 to 6. What do you mean by pI 4 to 6? What is the property? What happens at the pI? Protein precipitates, not all proteins, globulins usually, they precipitate, right. Why? Because you have mostly high electrostatic interaction and they just precipitate, right. Precipitation, some cases is very important for extraction, for example, precipitation is important. For aggregation, maybe precipitation is important, but some cases precipitation is not good. Why? Because let us say I would like to put this into some beverages, right, and the pH of that beverage is, let us say, 4, right, pH of the beverage is 4. What would happen if I use this protein? It precipitates. Do you agree? Now this protein is not useful in this beverage. Please note that food fortunately have a very good pH range. They usually, most of the food, what is the pH range of most of the foods? Slightly acidic. So basically if you take yogurt as an example, I don't know, pH is around 4, right? Some maybe fruit juices can come pH around 3, right? And then all the way depending, some alkaline foods are there. If you had a lot of garlic for example, so pH can up to 8, right? This is the range where most, I am not telling every food, most of the food have a pH range, let us say 3 to 8. Now, if you would like to use plant proteins, and it is important to note whether that particular protein can be used, because if the pH is changing, the protein is changing the behavior, you might get precipitation or you might get higher solubility, you never know, right. So, that is one of the things we have to keep it in mind, right. So, it is important to bring proteins that is more applicable in the food which contains a particular pH range. Now, we also discussed about this figure. Globulins were really good. They have a sharp sharp precipitation, but albumins usually they are crazy, right. They have a long solubility range. They do not want to precipitate. It is really good. In many cases, it is really good because plants usually food contains water, it becomes more soluble everywhere, we are so happy. But in some cases, we need to gelate the protein, right. We usually, how do we do gelation? How do we make cheese preparation? Rennet we add, or we do acid gelation, right. We add maybe citric acid to precipitate casein out of milk to separate casein and whey, right. And then the protein should have this property to gelate and to precipitate. Now, even if you add acid, I do not want to precipitate, then it might not be applicable in that particular application. Does that make sense? So, depending on the pH, depending on their solubility, sometimes they are advantageous in some application they are disadvantageous, maybe it is the wrong word, maybe it is not applicable. Make sense? So, now we need to change the properties of protein. Is it too boring for you, what I am telling? You are getting the point, right? I am trying to tell you why we have to modify. There is a lot of reasons why we need to modify plant proteins, okay. One more example here just to show, you can ignore this one for now, and you can see that digestibility of different proteins, right. We saw that usually soy is really good, highly digestible, but if you look into this, I think these are insects if I am not wrong. So, insect proteins, in this case at least, they were less digestible. Now, I mentioned in my previous case that insects are very sustainable, they produce very high amount of protein, extremely high amount of essential amino acid, even higher than plants, animals, but they are now less digestible. So, if I want to use them as an ingredient in the future, I need to make them more digestible. How do? I have to modify proteins, right. And then again we discussed about this, one of the biggest challenges today while selling the plant proteins, they are colored. Color is a problem. How do we remove the color? We need to modify proteins. So, just to summarize everything, I have given a background now. Protein modification is very necessary because protein modification changes the primary structure of the protein in some cases. In some cases, it changes the secondary, tertiary and quaternary structure, and that will give you the desired techno-functional properties. Am I clear? Protein modification is nothing but, in principle, it is modification of the primary structure of the protein or secondary or tertiary or quaternary structure. One important thing I must tell you that when I use the protein modification, we do not modify every single amino acid. Keep that in mind. We do not modify every single amino acid in food application whenever I use the word protein modification. Sometimes we just open up it just by heating, nothing has modified, amino acids are stable, right. In some cases I just modify lysine residues, in some cases I just modify serine residues very selectively. So, that will change the techno-functional properties. Are you aware of this particular point? Is it clear for you? Whenever I use the word protein modification, it's not the modification of every single amino acid. It's usually a minor modification when you compare the total amino acid composition, right? And that minor modification of protein perhaps changes the techno-functional properties. All right, so when we say protein modification, it is divided into three different types: physical modification, chemical modification, and enzymatic modification. I am using the word protein modification here in the food science world. Is basically we are intentionally modifying the protein. Okay, protein modification also happens in our body. Okay, and that is not intentional. I mean, the body does it automatically, but in our case, we are intentionally modifying the proteins using physical treatment, chemical treatment, and biological treatment, let's say enzymes, and that will modify the protein to get the desired modification. Please note that we are intentionally modifying here. You have a question, Asta? Yeah.
So you said that the modification can be in terms of means that a mild change in the amino acid sequencing, or it can be in terms of bond also, means breakage of few bonds and formation of new bonds.
Yes, exactly.
When we are talking about physical modification, chemical, maybe addition of or attachment of any other functional groups with the amino acid sequencing.
Yeah.
Right?
Yes, yes, you're right. Yeah.
In terms of bond and a little alteration in the sequencing.
Absolutely. So basically, I'll exactly cover this particular point in my coming slides. But since you asked this fantastic question, I'll try to answer, because maybe I over exaggerated what I meant here. So basically, you know, proteins are made up of amino acids, right? And some amino acids are bonded to another amino acid, what we call disulfide bond. Let's take an example, right? And we also know that there is an intramolecular hydrogen bonding. We also know that there is an intermolecular hydrogen bonding. We also know that there is a lot of hydrophobic interaction, right? These are the interactions stabilizes the protein structure. Remember my very first class when I was talking about protein structure, what are the bond stabilizers? I taught you some basics. So, yeah.
I want to ask, what is the basic bond which is present in the protein? Is it the peptide bond or the hydrogen bond, which is very much basic in the bond formation of proteins?
That's I mean, as again coming back to the previous
this
question.
Is something fundamental question I was asked.
The peptide bond is the basic bond.
Peptide?
The peptide bond. It's simply
Sir, I said this only, but they told I was wrong, and they said hydrogen bond is the basic bond.
It's, see, this is a chemical point of view, right? People have a different opinion. I'll come back to, I'll clarify you what do you mean by. Maybe it's a wrong question to ask, what do you mean by a basic bond in a protein, right? What do you mean by a basic bond itself? For me, as a chemist, it's a confusing question. But then I'll start explaining to the people, what do you want in proteins? What do you mean by basic bond? Do you want to know about the strongest bond in the protein? Oh, then it is a peptide, but it's a covalent bond. C double bond, O, NH, maybe it's one of the strongest bond that stabilizes the protein. Come back to my previous lecture. I told you that to hydrolyze that peptide bond, even if you heat it very high temperature, it doesn't break. You need to add a catalyst, H+. You need to add OH-, 110 degrees Celsius, 24 hours, even 7 days to break that peptide bond. How strong it is. Then we have these weaker bonds, what we call non-covalent bonds. Hydrogen bonding, hydrophobic interaction, van der Waals forces. There's a lot of other things stabilizes the protein. Usually these bonds are weaker. When the weaker bonds are present in a lot of quantity, they become stronger. Because even the protein is stabilized, even the protein is holded by hydrogen bonding, some proteins requires 80 degrees Celsius temperature to melt or denature. What does that mean? Those bonds are not that weak. Which one? The hydrogen bonds, the hydrophobic bonds, they are not weak. You need some degree of energy to remove that or break those bonds. So, to answer your question, the strongest bond is covalent bond in proteins, which is peptide bond, at least to talk about protein in general. But there are hydrogen bonds and they determine the secondary, tertiary structure and so on.
More to ask regarding this. You said that if a bond, if a protein is completely denaturing or breaking at the 80 degrees Celsius, right? When we talk about the thermal analysis
Yeah.
to characterize its thermal property,
Yeah.
if a protein is breaking at a very high temperature but
Yeah.
with low enthalpy,
Yeah.
then the nature of the bond present in that particular protein has a weak nature, right? So
Absolutely.
that's why less amount of energy is required to break those bonds.
Yes, it's very important to know that what kind of interaction present in protein. We all know that hydrogen can be if it is hydrogen bonded, mostly stabilized by hydrogen bonding. When you have a high temperature, hydrogen bonds are readily broken. But if it is hydrophobic interaction, when the usual temperature has an inverse effect, basically up to certain temperature, hydrophobic interaction will become more stronger and stronger and stronger when you increase the temperature. And
Okay.
beyond the threshold, hydrophobic interaction becomes weaker. It's again thermodynamics phenomenon, what you are talking about.
Wait, sir. What I can conclude from your discussion is that you're trying to say when there is hydrophobic bonds, then the enthalpy or the temperature required will be higher.
Yes.
And when there is hydrophilic interaction or
For example,
hydrophilic
hydrogen
bonds,
bonding. Yeah.
that requires small amount of energy that will be broken
Absolutely, yeah,
easily.
yeah. So
Okay.
this is the bonding
Thank you, sir.
thermodynamics, yeah.
That
Covalent
was
bond
very
is
much clear.
almost unbreakable unless you use radicals and something. Ionic bonds are almost unbreakable unless you use a solvent. Hydrogen bonds are very strong. They're weak, but very strong. For example, water is very strong, right? You need to heat it at 100 degrees Celsius to boil, to become liquid to gas. All this because of hydrogen bonding. There is nothing is holding two water molecules, just hydrogen bonding. They're so strong when they're present in too many cases, right? You need 100 degrees Celsius temperature. And then hydrophobic bonds are actually inversely proportional to temperatures up to certain degree, and then it becomes directly proportional. So it varies to the which residues involved in hydrophobic interaction and so on, proline and let's say aromatic structure. You know, I don't want to teach all these things today, but it's not my chemistry lecture. So there is a stacking interaction and blah blah, lot of interaction. You have a question, Niveta? Yeah.
Actually, covalent bonds are the strongest bond, no sir.
Yeah.
So this is disulfide bonds that are formed are
Yeah.
also covalent bonds.
Yes.
So if a protein has more of disulfide bonds, can we conclude that it will be tough to denature them?
No, that's very good question, and this is a very nice question. I'll also cover that in my previous question. Carbon-carbon bonds are strong. I agree with you. You can find out the bond energy of carbon-carbon in Google. Ask ChatGPT, it will tell you. And carbon-sulfur bonds having a lower bond energy. It's simply because carbon atom is smaller, maybe sulfur atom is bigger, and then you have small bonder energy. Then sulfur-sulfur bond is strong, but it's weaker than carbon-carbon bond because you have bigger two sulfur atoms, right? Now, to answer back, actually sulfur-sulfur bonds are very strong. It's not easy to cleave them just by heating at 10 degrees Celsius, 20 degrees Celsius, even 100 degrees Celsius. Just to give an example, you take cysteine. Cysteine is an amino acid having, cysteine is having one, you have cysteine, which is having a disulfide bonds. I did personally this experiment. I took cysteine in solution, I heated it at different temperature just to see if it breaks. When cysteine breaks homolytically, in a reducing pathway, you get two thiol groups, right? This can be easily measured by Illmann's assay, we know that, we can easily measure it. Now, I tried to heat it at a different temperature, nothing came out. Then I realized, oh, it's a very strong bond. Just by heating 100 degrees Celsius, it doesn't break. However, if you make heating in the alkali condition, change the pH, then you can have a higher degree of cleavage. Covalent bond was strong, temperature alone was not able to break, but if you change the pH, now the catalyst comes into play, then you can break. If you add a minerals, let's say iron and small amount of hydrogen peroxide, it will break, right? And proteins will also have a disulfide bond like this, intramolecular and intermolecular, but they are strained. They're such a bent in some cases, they are under strain, heavy strain. In cysteine, it's happy, just a single molecule, it's just lying like this one. But in some proteins, they may be very strained. When the bond is under strain,
Easily breaks.
it will break easily, right. So, maybe a mild alkali condition or a mild acid condition, a mild temperature perhaps cleave it off. Cleaving also takes place by different phenomena, it's not just breaking. You have a thiol disulfide exchange reaction, I will talk about that later. Lot of other chemical reactions happen that will break the covalent bond. You are not talking about a dry breaking of covalent bond, maybe that is the right word. There is a catalyst, there are enzymes, there are many things that indirectly break the covalent bond. Did I answer your question?
Yes. However, the peptide bond, it cannot be cleaved that easily. That's what.
Peptide bonds cannot, that was my previous lecture.
Yes.
Yeah, you need an acid, you need a base, or you need proteases. Just by boiling, no. It might cleave very slow. Maybe you need 10 days to cleave one peptide bond, or maybe 100 days, maybe 10 years. Some bonds are you need definitely heat, keep it for 10 years, it will break. Very slow. Make sense? Now, I did not answer Asta's question. So, you asked that what do you mean by, I told you that we will only minimally modify proteins, right, to get the techno-functional property. When I use the word minimally means, of course, we also cleave the peptide bonds, for example, partial hydrolysis. I'll talk about that then. We also mean that we will make up new protein cross-links. It's a minimal modification. It also means that we break the hydrogen bonding by boiling, by heating, by drying and all these things, just to let you know, okay. When I use the term minimal modification, it does not mean that I'm not breaking the bond, I'm breaking the bond. It also means that I'm making a new bond. Is it clear now? Very good question. Please ask such questions, then it is nice for me to answer, and let's have an interactive session. There is tons of different ways to modify proteins, and I copied this nice picture somebody summarized for me. And you can see that there is 3 different types of modification: physical, chemical and biological, and other types of modification which cannot be categorized. No, you will have the slides at some point. There is people are trying every single thing to modify proteins, but I am not having time to cover everything today. However, I will try to cover the most important things. Is that okay? The most common things we are following today. I promised to cover only chemical and enzymatic modification on the lectures, but when I was preparing slides, I realized that if I don't cover physical, it does not make sense, because that's also used quite a lot. That was my mistake on the slide, but anyways, I'll try to mix them together, then I'll get you a better understanding. Is it okay? So, let's start with the physical methods of modification. What do you mean by physical methods? Is basically we use physical things to modify protein. Light, radiations, heat, homogenization, anything else? Sonication, heating. Yes, exactly. We are not necessarily using chemicals or enzymes per se. However, using this physical treatment, we are changing the structure of protein, and that will lead to change in the techno-functional property. That is a physical one. No chemicals are added intentionally, no chemicals are added intentionally, no enzymes are added, no microorganisms are added here. But because of physical treatment, chemical changes can happen. Is it clear? We are not adding chemicals, we are not adding any oxidizing agent, we are not adding any reducing agent here. However, because of physical treatment, chemical changes in food can happen, in proteins can happen, and that is the underlying phenomenon of physical treatment. Is it okay? I will try to give some examples here. First one is heating. That is the most easiest thing to change protein property. When I use delta, delta means heat, okay, in chemistry. We all know that protein denatures when you do heat treatment. We have discussed that several times, and heat treatment is one of the common methods to get protein aggregates or gelates, right, that you have done it. Every protein has a different denaturation temperature that is unique, simply because following of Nivetha's and Asta's question here, they are made up of different types of bonds, different amount of hydrogen bonding, different amount of hydrophobic interaction. I use the word amount, it means the total number of bonds here, right, and that influences the stability, and sometime when you heat, proteins start denaturing slowly. They don't denature like this, right? It's a slow phenomenon. It's again a slow phenomenon. There are a lot of thermodynamics are involved here. It will denature slowly. And coming back to my previous example, our tryptophan example, right? Sometimes protein will have tryptophan inside, right? Hydrophobic components inside. You heat it slowly. What happens? Hydrophobic components comes out, because proteins are usually folded in a way that hydrophobics are inside. Why? Because it wants to interact with water, because world is made up of more water than hydrophobic substances. So, it wants to interact with water, right? Cytoplasm contains more water than unwanted things, right? So, basically that is the reason why proteins are folded in such a way that hydrophilics are outside, hydrophobics are inside. Now, you are heating, so they will open up, right? Then that hydrophobic moieties, amino acids, can interact with another hydrophobic moieties of another amino acid of another protein, hydrophobic interaction, and the protein can precipitate. Sometimes they can gelate, and that is good for in some application. That is one of the things. The second thing is coming back to her own question about disulfide bond, right? So, basically disulfide bonds and thiol groups are very crucial in creating protein structures, extremely important, very common basic things what we do. Let us say gluten has a stretchy structure because of this one, disulfides, right. The thiol groups will be, let us say, sometime buried, right. Thiol group is nothing but SH group. The protein will have a buried thiol group now. Okay. Now, I will write one chemical reaction. This is thiol group plus a disulfide group, right. I will write it as R1, R2, R3. When they come together, when there is little bit of pH, alkali condition usually, heat is not required, but heat will accelerate this reaction. So, when small amount of heat is there, then we have a reaction called thiol disulfide exchange reaction. Have you heard about this one? Thiol disulfide exchange reaction. Now, what happens is that this thiol group attacks the disulfide bond, and you create a new disulfide bond. Can you see? So, this will be R1 and R2, and a new thiol group is formed. Just keep this example in mind. And this reaction can happen within the protein, it can also happen between the proteins. Now, I have a protein with the thiol group, I have another protein with a disulfide, right. Now, this reaction is very favorable. Thiol want to react with another disulfide to create an aggregate. This will become an aggregate. This is protein number 1. This will be a protein number 2, it will become an aggregate like this following this reaction. Am I clear? Right. Now, you can see that two proteins are interacting and form a new aggregate, and that can happen with multiple things, and then they can become a big aggregate, right. Now, how heat is helping this reaction? If the thiol group is buried inside, it wants to interact with the disulfide bond. But to interact these two proteins together, the thiol group should be available. It should, otherwise they do not touch each other. When there is no touching, no chemical reaction, right. There should be collision between the molecule. So, now because of heating, you will slowly open up the protein and thiol group becomes available. Now, this thiol group interacts with the protein, another protein, and you get an aggregate if it happens with too many proteins. Is it clear? And that is how you are making and breaking the bond. You broke this bond, you broke this bond and you made a new bond. Can you see here? And heat is helping this reaction. Any question about thiol disulfide exchange reaction? Is it clear? It is one of the common protein modification we do in most of the food science laboratories, thiol disulfide exchange reaction to create aggregates. Okay. Now, just to show this table here, these guys took I think pea proteins here and cowpea proteins. What these guys are trying to see, to what percentage protein denatures with respect to heat treatment. You can see that increasing heat treatment increase the percentage of denaturation. I think the A8 and A10 was pH, if I am wrong. Yes, this is a two different pHs. So now you can clearly shows that by heating you can partially unfold the protein. When you partially or fully unfold the protein, it will allow for more number of chemical reactions. So heat is one of the methods to modify proteins. Easy, simple, just a water bath or a oven is needed, and it is also very scalable. Okay. Some practical examples here, you can clearly see that sometimes solubility is not changed and sometimes solubility is increased, sometimes solubility is decreased depending upon the heat treatment. It is simply because the type of interactions present among proteins. If it is hydrophobic, usually heat has generally no effect. If it is hydrogen bonding, maybe they becomes more and more soluble. It also depends upon you have whether albumins or globulins, right. So, heat can be used to improve the solubility. And here you can see that they tried to heat, was it soy proteins, exactly. They tried to heat soy proteins, and you can see that at 55 degrees Celsius and 85 degrees Celsius they heated the soy proteins. This is control, means no heat treatment. The foaming capacity was this much, and when they heated the soy protein, the foaming capacity increased. You remember foaming capacity? Remember that glass jar experiment, the foam formation? Foaming capacity is how far it will go in this direction, right. And that was also the case here. Did I copy the same thing twice? No. I am not sure what was this graph corresponded to. I do not recall this paper, I am sorry. So, it may be a concentrated versus isolate or something like that, but never mind, that is not important. But you can clearly see that foaming capacity in this case increased with increasing the heat load. Make sense? And foaming stability, and that is also dramatically increased. You can see that the foam was unstable, means it just forms, maybe it came down, but by heating these isolates here, the foaming stability increased up to 30 minutes. They could keep it, I think, in this case, and that is the amount of that is the percentage stability they found, about 80%. Is it clear? So, foaming stability can be improved by thermal treatment. Then a little bit about gelation. Heat treatment improves gelations. This is something we fundamentally do in our laboratories. I think many people have done least gelation concentration. That is a common approach we use. Basically, the minimum concentration of protein or treatment where we see gelation, that the thing does not fall down when you make it upside down. You can see that with respect to temperature, gelations are changing. So, just to give an idea here, you do not have to read all these tables, just to tell you that heat treatment can be used to gel the proteins. Okay. This is another example for emulsion activity, and they saw increase, in some cases no changes with respect to heat treatment. But the most interesting thing here is that, coming back to our anti-nutritional factor. One thing I wanted to highlight here is that when I use the techno-functional property in my lecture, I cover all the functional properties, plus I will also cover digestibility, flavor and anti-nutrients, and some people do not include that in the techno-functional property, but in my lecture I include. Is it okay? So, here you can see that by heating, basically they reduced trypsin inhibitor in this case activity. It is one of the very efficient method to inactivate proteases, heat treatment. That is what most of us do, and that is the reason why food has to be cooked. The reason why legumes has to be cooked before we eat, right? Trypsins makes proteins undigestible, because I taught this yesterday very in detail. I don't teach it again. Trypsin is an enzyme that hydrolyzes protein in your stomach. If there is another protein called trypsin inhibitor that interacts with trypsin and makes trypsin inactive. When the trypsin is inactive, it cannot digest the protein in your intestine, and you have indigestion, what we call, right. So, the protein digestibility will be compromised. By heating, you can kill or inactivate trypsin inhibitors. Lot of examples are there. I just found only one here for you. Okay. And I do not take all these other things. People also use ohmic heating and microwave heating instead of just taking the water bath to improve the functional properties. You can do microwave treatment and ohmic heating. I do not show anything about that, just to let you know that there are other types of heating you can do. Then I will go a little bit towards the gamma irradiation. It's in this case, the physical treatment what we are doing is light or high energy radiations, right? Gamma irradiation. Have you heard about gamma irradiation? So, I am sure you know this figure, right? The figure talks about the wavelength. It also talks about the energy, right? Light is a form of energy, right? Yes, right. Good. Now, if you look into this figure from left to right, the energy is increasing or decreasing? Left to right. Which one is more energetic radiation? Is microwave radiation is energetic or gamma radiation? Gamma radiation, right? Gamma radiation is highly energetic radiation. Please, I mean, I do not teach you chemistry again. Waves or the light can bring some changes in food, right? For example, radio waves have, people say they do something, but usually they do not do anything, because they can't change any chemical thing, right? Then we have a microwave. What does microwave do? They rotate the molecules and you get heat. For example, you can make your coffee hot very quickly in the microwave, right? Then we have infrared. They are the heat radiations, right? What chemical changes they bring? They can vibrate, they can make bending of the bonds and so on, that you have studied in the FTIR last time. Then we have visible light. They absorb light. For example, we are all colored. I am white. No, I am not that white. I am sorry. So, we are fair and I have black hair and somebody has a white hair. Milk is white, or anthocyanins are purple, because they absorb light, visible region. Then you have UV light. They kill bacteria, more energetic, right? Then we have X-ray. X-ray has a very high penetration power. So, you go and fall on under X-ray machine, they can see your bones, right? Because it passes through the muscle, but may not be through the bone. So, then you get the bone cracks and so on. They are very energetic, X-ray. Then gamma radiation comes after X-ray, means it is extremely energetic. It can bring a lot of chemical changes. Am I clear? Gamma radiation is extremely energetic. It can bring lot of chemical changes. It can break the bonds instantaneously. Okay, it is so energetic, it can break the bond, it can knock off the electrons. So, that is the gamma radiation. The mechanism of gamma radiations, I do not teach you a lot here, just to show you that when you have radiations, they can do homolytic cleavage of water molecule, then you get hydroxyl radical and hydrogen atom. I think in one of my previous lessons I mentioned to you is that hydroxyl radical is extremely reactive, very oxidizing in nature. It will oxidize everything, proteins, lipids, carbohydrates, whatever it polyphenols, it will just oxidize. Okay? It can interact with proteins, can oxidize proteins and can hydroxylate proteins. Now, the original protein was like this. Okay? Now, if I have a hydroxyl radical formation and that can add it to the protein ring, and then I get a new protein with OH group added. Now, in chemistry you know that OH groups are polar, right. So, now it gives you another property to the protein. Am I clear? And we also know that OH groups will make hydrogen bonding. right. Originally this protein was not capable of making hydrogen bonding, because it does have only aromatic, for just to give an example. Now because of this gamma radiation, I created hydroxyl radical, and hydroxyl radical can attack proteins and can hydroxylate protein. Hydroxylation changes the polarity of the protein, can increase the hydrogen bonding tendency. Now the protein-protein interaction can be changed. When the protein-protein interaction changes, functional property will be changed, the digestibility will be changed, so many things will be changed. Is it clear? I just give one example. They can also do a lot of other things. They can make protein carbonyl formation, for example. Many things these radiations can form. They change the primary structure of protein. Please note down that gamma radiation can change the primary structure of the protein, and change in the primary structure will change the secondary, tertiary, quaternary, at the end of the day, complete functionality. Any question? Yeah, gamma radiations will change the primary structure of the protein. You can see just example here. Originally there was a phenylalanine here, right? It was phenylalanine. Now I made a tyrosine out of phenylalanine, right? So basically you are changing the primary structure of the protein. By changing the primary structure of the protein, you change the secondary structure, because secondary structure is dependent on the primary structure. Tertiary structure is also dependent on the primary structure. So the protein folding and unfolding behavior changes, hydrogen bonding changes, hydrophobic interaction changes, the techno-functionality, digestibility will be affected when you do irradiation or gamma treatment. Clear? Absolutely, that was I mentioned in the very first slide. Physical treatments are physical treatments, but they bring chemical changes, right? They are all chemical, no, okay, I will try to answer it in a different way. My original graph, maybe we can do it in a little different way. When I use this particular classification, this classification what I used based on which method you are using to modify, to initiate the product, okay. Is that clear now? But as I have clarified it already actually, when I say physical modification, it means we use physical treatment to modify proteins, and they can bring chemical changes. Is it clear? When I say chemical modification, we will use chemicals to modify proteins, and they will bring chemical changes. When I say biological modification, we will use enzymes and bacteria to modify proteins, and they bring chemical changes again. Chemical changes will happen, otherwise protein will not change, right? Chemical changes is important. Now I am clear, hope. So physical modification does not, I mean, maybe I have to correct my way of teaching my English here. So it basically brings chemical changes, okay. Any question? Just to give one example, just to show here, I mentioned about they change the protein structure. Remember my lecture number 3, we talked about UV fluorescence spectroscopy to see the modification of the protein tertiary structure, yes. I think they are trying to do this one, they are doing the tryptophan fluorescence if I am not wrong, yes. You can see that this was control, no irradiation, and this one is irradiation. They use different intensity of gamma irradiation. I think GY is called gray, right? They measure it based on gray, right? Gray, yeah. For example, how to say? It's a unit of irradiation. It's gray for gamma irradiation. Okay, so you can clearly see that we are having a red shift, right? The protein having its red shift. What do you mean by red shift? Was it hydrophilic, becoming hydrophilic or hydrophobic? I forgot now, you have to go back and see my slide back, right. When you see a red shift increasing the wavelength after treatment, that indicates proteins are exposed or proteins are not exposed. The hydrophobic region is exposed or hydrophobic regions are buried. I don't remember. It's like red shift means unfolding. So you can clearly see that the protein is unfolded. Can you see? Now it's a red shift going toward the higher wavelength, the protein is unfolded. Exactly the same mechanism which I mentioned to you here. You are changing the primary structure, protein unfolding takes place, and you have a new protein basically here. And here is a nice example, they show how you can change the techno-functional properties. One of the good things you can observe, don't read all the diagram, all the words, all the values here, it's not interesting. Just look into the conditions here, they are increasing the dosage here, right. They are increasing the irradiation dose, and you can clearly see that the oil binding capacity is increasing, okay. Emulsion activity is increasing, oil in water. Emulsion stability is increasing, okay. Water holding capacity is somewhat decreasing. This is decreasing, right. Now, can you correlate this one with this one? What is exactly happening? What kind of protein structural changes changing? Can you give her a mic? Yeah. Yeah, it's okay.
Hello?
Yeah.
More hydrophobic moieties are exposed.
Do you agree with her? Because now in this case we confirm that irradiation increased the protein unfolding. Now something is coming outside now they are more available. Now she is telling, because she clearly saw all the oil related stuffs are increasing, right. Oil holding capacity is increasing. What do you mean by oil holding capacity? My previous lecture, ability of the protein to bind to oil molecules, let's say triglyceride. Triglycerides are oil, loves hydrophobic region. So it indicates that maybe more and more hydrophobic regions are exposed, so that is increasing. Clear? This is something similar, same data but from another paper. And here they can see that it's from another paper, they show how emulsification capacity, how emulsion stability and protein solubilities are changing with respect to gamma treatment. In this case, increasing the radiation dosage increase the solubility of the protein, again probably because you are getting more and more hydroxyl group, or you are making more and more carbonyl groups because of the protein oxidation, and they will change the solubility of the protein, and that you will see here, right. When the protein solubility changes, all our emulsion behavior and everything will change, okay. In this case at least they saw increasing foaming stability with respect to increasing radiation dosage. Again I am repeating, don't worry about this all bar graphs, just remember the take home message. Take home message is gamma radiations will change the protein primary structure, right. They will make proteins perhaps more polar, or they expose more hydrophobic region, and that will change the techno-functional properties. Another very interesting thing I found is that in that paper they also showed that you can increase the protein digestibility by gamma treatment. Can you tell me why the digestibility perhaps increased?
The anti-nutritional factors will be inactivated by the...
Absolutely, maybe one of the reasons anti-nutritional factors may be inactivated or degraded or destroyed because of the gamma radiation. But imagine I am ultra pure, 99.99999% pure protein, what would be the reason? What's that? Proteins are more into the smaller units, maybe that is how the gamma radiation is improving digestibility. Come back to the same thing. Yeah, Asta, you have a point?
So as it is exposing the hydrophobic regions, and maybe the assimilation with the fat, it can be the protein can be digested faster.
Absolutely.
It can be the probable reason.
There are many, there is no direct answer for this question. There is a lot of reasons. One, what Nivetha mentioned here, what Asta mentioned here. So basically, there is a lot of reasons why the digestibility increases. One of the fundamental reasons could be protein unfolding. Unfolded proteins are apparently more digestible than the folded proteins, because usually that is plant proteins are less digestible simply because there is high degree of folding, right? And now you unfold them, maybe they are more accessible to enzymes in the stomach, in this case in vitro protein digestibility, though it is more accessible to enzyme and you will get a better digestion. And also because of protein, because of gamma irradiation, protein can also be cleaved. Okay, peptide bond can also be cleaved because of gamma irradiation, and then apparently the digestion will immediately increase. Okay, you have any question?
Does that not denature the protein? It will denature.
It will
the-
denature. Denaturation by default, that is a primary effect. When you change the primary structure, denaturation is you are expecting. It is another example here how the gamma radiation is improving reducing the allergenicity. You can clearly see that the percentage inhibition when you use the gamma irradiation. That is fantastic, right? It is one of the biggest challenges, allergenicity. You can use gamma irradiation to remove the allergenicity. Now, I will have ask a question. I told a lot of good thing about gamma irradiation, right? How it can do many things. It can improve digestibility, it can improve emulsification, foaming, blah, blah, blah. What could be the disadvantage?
No regulatory standards.
There
for
is no
applying.
regulatory standards. Yes, you are a very good point you raised. However, in Americas, in the USA, gamma irradiation is allowed, but not for the protein modification, I don't know, but they use gamma irradiation to kill the bacteria on the surface of some food products. In the EU, it's kind of regulated. In the US, they use it a lot. For example, they use, I'm on camera, but I think they also use it for meat, if I was not wrong, to kill the surface bacteria. I'm not very sure how to read my article, but I remember like that. Okay, I might be wrong. But that is kind of approved in the US, but I don't remember it is approved for the protein modification per se, because the rules changes. They also specify which food products can be allowed to modify with radiation. When I say radiations are allowed, it does not mean that they can use it for every single kind of food. No, that is not the regulation. Regulations are usually specific to certain food commodities. Okay. Another disadvantage, yeah.
When we talk about in terms of safety, we are inducing any rays in the food product
Yes.
to cause some changes,
Yes.
to improve its techno-functionality.
Yeah.
But there is a con side of this, that there may be possible, means after doing the safety evaluation only we can come to a conclusion that these rays may result in the formation of some toxic components whose effect on human health can be negative.
Absolutely.
There is possibility of formation of toxic
Unwanted
components.
components
Yes,
or
unwanted.
potentially toxic molecules that can generate, because my idea was to improve the solubility. I am very happy that the solubility is improved. Now I will give it to this person, gentleman, eat my protein. Now it is very soluble and he will eat. I don't know, he might die very soon. I am sorry, just to give an example. So these things are the problem, right? Don't take personally, just just an example. In fact, I am doing research on this particular topic. That is my core area of research at the University of Copenhagen. I am trying to investigate how this physical and chemical treatment, because all my colleagues or other part of the world, they are all focused on, oh, digestibility, oh, techno-functional property, oh, I have to improve this one, oh, I have to decrease this one. Okay, what about the chemistry you are doing? You are changing a lot of chemistry here, right? But we are focusing like this, right? Oh, I just want to improve the solubility. I don't care what else will happen. But many things are happening because chemistry is a very crazy thing. It is not selective to one amino acids usually. They will start damaging so many things. Protein is so complex, right? And I am trying to investigate what kind of harmful compounds are formed during these irradiations and so on. And I am trying to feed to animals and see if the animal dies or it becomes super happy or it becomes super crazy. So those are the investigations. I am not telling they are bad, huh? Please note that. We don't know. Yet there is less toxicological evaluation on the protein modification. There is one thing I have to keep it in mind, because when I say the treatment of whole food, it is a different story, because then they treat on the surface. Let us say you take broccoli as an example. You want to kill the bacteria on the surface of broccoli, right? It is a vegetable, right? You are just doing the treatment on the surface. Now, if I want to treat, this is broccoli, okay, then I will apply the gamma irradiation here, right? Now, in our case, what we have to do to modify the functional property, we need to take it in solution. Do you agree? Now, the protein is dissolved in solution. The chemistry what happens here is very different than the chemistry what will happen here, because now more and more molecules are interacting with the gamma radiation, because gamma can penetrate through solution. It can attack almost all protein molecules now if you put a good intensity or good gray here. So, the story are different here. So, if the gamma can be used on chicken fillets or broccoli, gamma may not be useful on your protein ingredients, because the way that is being treated is different. When the way you treat is different, the chemistry is different, toxicology will be different. Any question? Yeah.
Just to add on to this, many toxicological assessments are going on when we are treating the food with different types of processing
Yeah.
techniques,
Yeah.
right? And there is possibility of many scientists have exposed that nitrosamine, heterocyclic carbonamines,
Yeah.
acrylamide, they have been produced in the food products due to the different kinds of processing and the interaction between the food matrix, because food is the complex matrix.
Yes.
Composed of protein, carbon, fat, lipids,
Absolutely.
phytochemicals. So this can be the possible reason, and the way you said that you are doing a project on this means that project is basically focusing on the chemical reactions which are being going on in the food protein after the modification.
Absolutely. Yeah.
So that will cover the toxicological assessment part
Absolutely,
also.
absolutely. So we are, I mean, I have I have two projects running on that one at the moment. In one of the projects, I'm trying to investigate the chemistry, exactly only chemistry basically, what exactly modification are happening in the presence and absence of other molecules, what happens when metal ion is present, whether it will change, because food is complex as you said. Another project we recently received, we are trying to see this modification plus the brain effect, as I was telling last time. So, you eat a lot of these modified compounds, whether you can memorize my Gan lectures or you will forget very next day. The food is your brain, right? So, there is a nice connection. So, I am trying to investigate.
Hippocrates have said that we are what we eat,
Yes,
right?
exactly.
And
we are what we eat.
Very much
Yeah.
being correlated. And in our, in fact, Shushruta or in our ancient Indian history also, many of the Ayurveda believe that we are exactly what we eat. So that's why in the beginning of that first lecture, I said that a person who is more mindful in their eating pattern or the eating diet, so they are more concerned about the emotional quotient also of the food product they are consuming. So that's why many of the people are becoming vegan
Absolutely, absolutely.
in this
And also
era.
they talk about minimally processed. I don't like to eat processed food, maybe because of all these reasons, right? And the problem is that on a consumer point of view, they have no idea about what type of processing has been done on the product they are eating on, that's on their plate now, right? We believe everything is good as long as it's packaged and as long as FSSAI seal is there, FDA seal is there, we think okay, it's maybe good. But there is more to study here basically, right? The food is very complex, lot of things, other things are happening. But again, I want to tell you, emphasize one thing, processing is not bad. Please keep that in mind. Processing is not bad. Processing has to be done. This may be a minor reaction, you never know. Right? This could be absolutely a minor reaction. Even if you eat 100 grams of protein, maybe you are getting the toxic compound very small amount. Our body is so efficient to excrete off. But that has to be investigated. Somebody has to prove it, right? But that is something is lacking at the moment. The research is going in that direction. Am I clear? I would suggest to take a break now. So we will take a 15 minutes break and we will resume at 11:15. Okay, we will take a break. We will take a break and we will back at 11:15. Okay. Okay, let all right. So, welcome back everyone. So, we are still continuing with the lecture number 12, chemical and enzymatic modification of proteins. We have discussed about physical modification technique, especially radiation, gamma radiation, how it can be used. And now we will move on to the other technique called UV radiation. Before I start my other part of the lectures here, I must have to mention that I have been discussing with some of the friends here. This lecture requires little bit chemistry background. This lecture requires little bit chemistry background. Because I am going to talk a little bit about chemical modification and so on, and I also know that some of you might not be having that much chemistry that in your bachelor's, studied in your bachelor's or master's. So, you might find this is a little bit overwhelming, but do not worry. The important thing for you here, those who are sitting here, is that at least look for the take home messages. At least think about what are the different technologies are present. Since this lecture is being recorded and I cannot make it too simplified, because maybe some other people it will may be useful. In the future you might have to find it very useful. Then you come back and go to YouTube and see my lecture. Oh, sonication, oh, this is what happening, right? And that is the reason why I will not too dilute my lecture, but I will not make it too complicated either. I will try to teach you the basics, okay? If you do not understand, do not hesitate to raise your question and ask me to explain again, okay? So, UV radiation is something similar to gamma radiation. In case of gamma radiation, we use the very high intensity, very high energetic radiation. In the case of UV, it is energetic but less energetic than the gamma radiation. Basically, we use a UV light, and UV light has a wavelength between, let us say, 200 to 400 nanometer, and at this particular wavelength the light, the photons are sufficiently energetic, they can excite the electrons, right. UV light is sufficiently energetic, they can excite the electrons from one orbital to another orbital. This is something we have studied in our previous class when I was talking about fluorescence spectroscopy. You remember this diagram? Right? The electrons were here and it went here by absorbing light. You remember my Jablonski's diagram, it is called, right? So, basically UV light can bring chemical changes by exciting electron from one orbital to another orbital. I will not teach it so detailed considering your background, but I will give you brief information how exactly UV can bring changes, okay, very briefly. So, these are the three different energy levels, let us consider, okay, different energy levels. Now, I have two electrons here. This electrons belongs to protein where the amino acids having aromatic structure. What are those? What are those? Phenylalanine, tyrosine and tryptophan. Phenylalanine, tyrosine and tryptophan, these are the three amino acid residues on protein. They are UV active, they are photosensitizer, that means they absorb UV light and can go to higher energy state, Okay, that is their inherent molecular property because of the aromatic rings. Am I clear? Just remember that on a protein there are 3 amino acids, tryptophan, tyrosine and phenylalanine. They are UV active. That means they can absorb UV light. When they absorb UV light, they can go to higher energy state. Now, imagine these are the 2 electrons of tryptophan. Just imagine it absorbs light. Which light? UV light. Let us say it is absorbing at 280 nanometers specifically. Now, there were 2 electrons like this. These were the 2 electrons. Electrons are oppositely spin now. Now, you apply UV light. What happens? Tell me. First step. Electrons will absorb the light. Light is a form of energy. So, it will go to higher energy state. How long it will go? It depends upon how much the energy it has absorbed. How long means how many orbitals it can cross, right. So, imagine it absorbs UV light and it went to higher energy state here. It is called excited states. Okay. And here the electron spin is the same. Spin means now these are oppositely, the spin of electrons are opposite in an orbital, that Pauli's exclusion principle and all these things I do not teach. So, it will go to higher energy state without changing the spin. Spin is the same, means it is rotating now parallel or anti-parallel, it will not change. Okay. Now, what are the possibilities? What will happen next? I can give an annotation. Come back. So, just to give an example, I was giving an example last time. You are at home, imagine, in the evening, and you are tired and you got some energy and you want to went to terrace, right. You will enjoy in terrace for a couple of minutes, couple of hours, but will you sleep at the terrace? No. You will come back to home, right. Like that electrons also will do. When they take some energy, they go to higher energy state and they will come back to home. But while coming back to home, if I were like, there are a lot of steps, right, from terrace there is a lot of steps. There is a lot of possibility how you can come back. This is you are inside, you went to the terrace, right. And while coming back from home, back to the home, to your room, you can do it in multiple ways. One, from the terrace you jump directly, right. From the terrace directly jump directly, that is one of the possibilities. Second possibility, from the terrace you jump to the sub terrace, because usually there will be 2 terraces in homes, right. From the first terrace you jump to second terrace and then jump back to the ground floor. Second possibility. Third possibility, from the terrace jump back to the second terrace, then take the stairs. Third possibility, right. So, electrons can also do in a different ways, they can come back to the ground state. One of the possibilities, they take the energy and suddenly can jump back the state, but energy levels are divided into vibrational energy level. So, basically they come back to the another energy level by releasing the heat radiation. I have taught you before already, right, and then they can come back to the ground state. And what is this? By emitting the light back, what is this phenomenon called? Fluorescence, that I have taught. The fluorescence spectroscopy works exclusively on this phenomenon. Did any chemical reaction happen here? No chemical reactions has happened, remember, it is only physical phenomenon. Light has been absorbed, heat has been reloaded, remaining light has been released, it is just a physical phenomenon. But some cases chemical phenomenon can happen. What will happen? The electrons took the energy, okay, you got a cup of coffee, okay, now you got energy, you went to the terrace. In reality, you should have come back to the ground state, that is to your home. What you will do? You got a crazy idea on the terrace, okay, you will stay in the terrace for a few more minutes there, okay. You get a lot of crazy ideas. You can bring another friend together with you, you can fight with him or her, right. Lot of things can happen on the terrace now. And the electrons also like that, crazy. They really wanted to come back to the ground state, they do not want to come back. I will stay in the terrace for a while, what they will do, they can ionize, that means they can disappear now. The electrons, instead of coming back to the ground state, they can ionize. The molecule, the tryptophan can ionize. Now the tryptophan was originally like this one, with a good number 1 electron, it releases an electron, okay. That is called ionization. We call it as photoionization because of the light, right. Now tryptophan is surrounded by oxygen. For example, you take a protein in solution, there is always water and oxygen, there will be dissolved oxygen every time in food, right. Electrons loves oxygen, or oxygen loves electron, and oxygen becomes a new molecule called superoxide radical anion. Superoxide, have you heard about it? Superoxide radical anion is an oxidizing agent. It can oxidize some other molecule. Am I clear? This is one of the possibilities. The second possibility, again coming back to the terrace, right? You went to the terrace like this one, you should have come back, you did not come back. While coming back, you will not jump to your own terrace, you will jump to other home's terrace. You are becoming monkey now, right. So electrons are also having an overlapping orbitals or shells here. They should have come back to the ground state, right. Instead of coming to the ground state, they jump to the other orbital by changing their spin. That is like you went to the terrace, you should have come back. Instead of coming back to your home, you jump reverse like a monkey, changing your spin, and then you will come back to the ground state, and that is called phosphorescence. You know, heard about phosphorescence? And this will take little bit time. Why? Because you have to went up, instead of coming back to your home, you went to others' home terrace, and then you came back to your home, and that takes time. Usually fluorescence is delayed. Radium watch, you know, you get the light in the night, that's fluorescence. Now that is the second phenomenon is happening, but sometime what happens, while jumping back from the electron, they actually interact with other molecule. Somebody else is on the terrace, they react with them, and they can generate another superoxide radical, and sometimes they transfer their energy to other oxygen molecule, become singlet oxygen. I don't teach this all this thing in detail, it's not required for my today, but just to let you know that because of this light transition, you get reactive oxygen species. Can you see? These oxygens are highly reactive, they can oxidize proteins. Did I confuse you? It looks super complicated, right? It looks super complicated, but you have to watch my video back, you will understand it, right? You will watch my video back, you will understand it. Simple, I will explain briefly in next 2 minutes. Electrons were ground state, it absorbs energy. Went to higher energy state, 2 possibilities. It can come back to the ground state by emitting the radiation back, fluorescence. Second, it can change the spin and then emit the radiation back, it called phosphorescence. Fluorescence and phosphorescence are physical phenomenon, no chemistry is involved here, and that is what we use it in fluorescence spectroscopy, forget about it. However, certain cases chemical thing can happen. It went to higher energy state, some molecules instead of coming back to the ground state, they ionize, releasing the free electrons, free aqueous electron in solution, and that electrons will be grabbed by oxygen molecule, oxygen becomes superoxide. Oxygen is very electronegative, it likes electron because of its orbital lacks electron, it has a space. It takes that electron, becomes superoxide radical anion. Superoxide is a ROS, reactive oxygen species, it can oxidize proteins. Second possibility, instead of coming back to the ground state, they change the spin, and then they will interact with other biomolecules, and then will become another, they will knock out the electron, becomes another superoxide radical, right. It is called type 1 for, no, it is called type 1 or type 2, I forgot, anyways. And in some cases they transfer energy to oxygen, the triplet oxygen can become singlet oxygen is also very reactive, it will oxidize proteins. Take home message is, light can bring chemical reactions now. It was purely physical if it is fluorescence and phosphorescence, now the light is bringing chemical reaction, and when the chemical reaction takes place, protein will modify. When the protein modifies, structure is changed. When the structure is changed, functionality will be changed, digestibility will be changed. Now this is just an any question here? I am telling you, watch my video again. I don't want to explain this again. It's a little bit complicated, but when you need it, just watch it again. Okay. All right. Now, just to show you that you can clearly see that how the light treatment will change the gluten structure here. You can see this is where the proteins are supposed to absorb. There is a change in this. Those secondary structure can be changed. And here they show that UV treatment actually increases the thiol group in gluten. It's simply because when you have a disulfide bonds on a protein, because of the UV light, through different mechanism, I don't teach all this mechanism, you can get more thiol groups. Clear? So, disulfide bond can become thiol group because of UV treatment. Exactly the same mechanism I showed you, it forms reactive oxygen species. Sometimes disulfide bond can directly absorb the light, they can be cleaved. So, it becomes more and more thiol group. Okay. So, increased thiol group means maybe increased thiol disulfide exchange reaction, you can get more aggregation or less aggregation. Is it clear? Another nice interesting paper I found that they found that gliadin is an allergenic protein. By UV treatment, the allergenicity can be reduced. By UV treatment, allergenicity can be reduced. If you really want to learn more about irradiation, light, UV, gamma, how it affects techno-functional properties, try to read this nice paper. Okay? When you are free, just read this review article, there is a lot of information about it. Any questions about UV? Yeah. It's a UV, now I completely forgot the ranges here. Basically, UV has 3 ranges, right? UVA, UVB, UVC. Do you recall what is the UVC range? I don't recall, but I can tell you that it is between 200 to 400, and they are divided into UVA, UVB and UVC. I don't recall, I don't want to tell you that because I might be wrong, but I know the numbers, right? Basically, 254 nanometer, which will kill the bacteria because they will damage bacteria's DNA. I think it's UVC, I am not sure, right? So, we don't use it very low intensity UV 200 for example, because they are highly energetic, they create unwanted reactions a lot. Okay? We try to use it around 280 because we will selectively excite tryptophan in food science. Am I clear? You are welcome to use any range you want. We don't want to use 400 either because then it is a very weak energy. You don't excite tryptophan, it is useless. Because tryptophan has a absorption maxima like this around 280 to 295, something like that. So, you don't use 400 either. So, it is basically 250 ish we use, 250 to 290, 300, something like that. Is it clear? But I don't know the classification, I forgot, but that is readily available in Google. Okay? Any question about UV? Please note that UV is kind of approved in some cases, it's historically used to kill bacteria, because you know microbiology laboratory, there is something called laminar airflow, they turn on the UV light and go home, no, they come back after 10 minutes, right. What do they do there? They turn on the UV light because the UV kills the bacteria by denaturing the proteins, they change the linkage between purines and pyrimidines and all these things, right. Same thing is happening with proteins. It just modifies, degrades proteins. Am I clear? And that said, again coming back to Asa's question, this can also create unwanted chemical modification because protein oxidation could be bad, could be not bad, could have some techno-functional properties, could change something, could create unwanted chemical moieties, could have a different health effect. No much research on this area, and that is something I am investigating in my own lab. How UV is modifying proteins and how it is creating some unwanted molecules, to what extent and what happens if we eat them. That is also our area of research. Clear? Take home message is you can use UV to modify, but be careful. Now we will move on to sonication. I think I taught this on the day 2, ultrasound assisted extraction, right? Remember the mechanism? Can anyone dare to explain me the mechanism? It is sound waves. Yeah, you can pass a mic to her.
It's a sound wave.
Yeah.
It moves. While moving, it has a compression
Yeah.
and it's have a retraction,
Mhm.
and it creates micro bubbles or small bubbles. When
Yeah.
it implode, it will interact with the cell and cell damage happens.
Exactly. So, ultrasound is nothing but we will use high intensity, low frequency ultrasound radiations, and these high intensity, low frequency ultrasound radiation, when they are propagating inside a solution, they create a small vapor filled bubble because of the movement of the wave, contraction and rarefaction, compression and rarefaction, basically negative and positive pressure between the solvent molecule, then you get a small micro bubble. The bubble will increase the size as soon, I mean continuously you are applying the sonication power here. At some point they implode. When they implode, they release energy in the form of heat up to 5000 degrees Celsius. Pressure will be very high, and at very high temperature, it is happening not completely in a small portions inside the solution, it creates a microjets, and that microjets can explode the cells, okay, and that can change the extraction behavior. That is what we have studied, but that can also do some chemical changes, because some people say during sonication you can have homolytic cleavage of water molecule, it will give you hydroxyl radical plus same as before. I do not believe this because there are some proof, I have to believe it. There are some proofs, but it might be not as efficient as gamma radiation, just to let you know. It is not as efficient as gamma radiation, it can produce. And I have already discussed about how hydroxyl radical can damage proteins, and the damage have a different functional properties. Is it clear? And some people also say that it will change the hydrogen bonding and other things simply because sonication is always associated with heat, right. When you know your water bath, you turn it on for half an hour, it becomes hot, right. Sonication is associated with heat, and heat will change the protein structure, which we have already shown in my first part of the lectures. Is it clear? So, please note that sonication is very unlikely to bring a direct chemical changes. It is not that efficient to bring the chemical changes, but it will indirectly modify the protein. Indirectly by releasing the heat or by releasing the hydroxyl radical. Am I clear? Sonication will not bring direct chemical changes because it is a very weak waves, very less energetic waves. So, molecules do not have a chemical changes because of ultrasound, it is just a sound waves. Am I clear? So, there are some studies, they clearly show that you can change the secondary structure of proteins by sonication, and they can show that you get the increased water holding capacity by sonicating the proteins. You can decrease the turbidity by sonication. You can change the water holding capacity, this is emulsification, you can change the water holding capacity. It is simply because when you do the sonication, because of the thermal effect or because of the oxidation effect, protein will denature, more exposure, more interaction, that is it, right. And why turbidity changes? Reduction in the particle size. So, you can use ultrasonication to do these things. This is a nice paper I saw. They found that ultrasonication inactivates trypsin inhibitor, which is super cool, because trypsin inhibitor is a inhibitor of the digestion. So, that can be solved, that problem can be solved using ultrasound treatment, okay. And they are showing that increasing I think, I am not sure whether this is a treatment time or something like that, that decreases the trypsin inhibitor activity. The same paper, they also showed us that ultrasound treatment increases the protein digestibility. Again, something related to exposure of the amino acid, denaturation of the protein, right. It is not so efficient, you can see that they were at around how much is this? Maybe 75, and they reached 80. It is a poor way of representing scientific data according to me. They are just we are just trying to hype it, right? It's only a minor change, but we cut down the axis. Can you see? You're not allowed to show axis like this in scientific diagrams. You should show from 0 to 100 here, right? They're trying to show the comparison here, and that's the reason they want to show the it. For me, it looks like, oh, there is a lot of change, but in reality, it's only a minor change. Am I clear? So whenever you make a scientific diagram, don't oversell your data. Tell the facts, right? You don't have to tell that ultrasound increased digestibility significantly. Yes, there is a significant increase. From D it becomes A, right? Statistics show significant, but in reality it's maybe a minor change. Am I clear? So don't take home message is not that ultrasound will dramatically change the protein digestibility. No, I don't believe. Small change might happen. Another beauty of scientists is, I must have to mention here, we will only publish when we get a good result. Do you agree? We will only publish when we get a good result. We dare to not to show the negative result. That's the problem of the scientists, especially the PhDs, and including me when I was a PhD student. If there is no digestibility change, I would not put that data on my paper. People think the reviewer will be unhappy, oh, no change in the digestibility, why the hell I am doing this sonication experiment. It's a bad, yeah, exactly, it's a bad idea of doing that one. You are, as a scientist, you should always show good and bad, because now I am teaching these lessons, I am trying to find some articles, everybody is showing only positive thing, nobody is trying to show the negative thing. Out of 100 cases, maybe 80% cases digestibility did not change, maybe it's even reduced after sonication, right? So when you do not only sonication, I am telling about all the treatment we are doing. So try to show both positive and negative result. Don't believe in only positive result. My lecture is going in a way that I am only showing, oh, trypsin inhibitor activity increased, oh, digestion is increased, oh, foaming capacity increased. Maybe 10 out of 100 this is the case. Out of 80 is nothing is changed, maybe it's changed negatively. That's also another take home message. Am I clear? It's not necessary that the treatment will always improve the functional property, it might not do anything. That is the case of PhD student. I have a lot of people working like that. They come and say to my, Mahesha, I tried so many things, nothing is working. Okay, now increase the temperature. Oh, now increase this one. Still nothing is changing. It's a common thing. Don't worry, okay? Now extrusion, yeah, Nivet has a point, yeah.
Is sonication always associated with the generation of OH?
No. It's okay. Where is that diagram? Okay, here. When you put it will not happen in bath system. Bath is very weak. In the probe system, what happens? You have a probe here, and you have water molecules on the side, and basically it is sonicating like this with a very high power, basically. And the surface of this probe, there is a high chance that there is a high intensity implosion, and that generates, let us say, 5000 degrees Celsius or Kelvin, it is the same now because it is so big number. 5000 degrees Celsius is too high in reality, but it cannot break the covalent bond in principle. Even at 5000 degrees Celsius, you can't break some of the covalent bond, but the pressure, I think it goes to 50 megapascal. Now you have a high pressure and high temperature together, and then there is a chance that you can have a homolytic cleavage of water molecule. And there is a paper published in Science. Science is one of the famous journals, and they measured the temperature near the after sonication. They proved that it goes to extremely high temperature, but it is not happening in throughout the solution in a particular regions, and then you can have a homolytic cleavage. And we did a lot of experiment to prove hydroxyl radical formation. I did not see personally, but there are some paper they show hydroxyl radical formation. It's not always the case. It depends upon the intensity of the radiation you are applying. It's very difficult to measure hydroxyl radical also because they are highly reactive. They just disappear. As soon as they form, they disappear, because they attack another biomolecule and so on. The half-life is very, very short. But if you use the technology called ESR, electron paramagnetic resonance, or there are some probes available to capture hydroxyl radical, they confirm that hydroxyl radical forms, but not to a very high extent, a little one. But little could be enough to damage protein, just to let you know. Did I answer your question? It's not always, but some cases, yes. Some extrusion, I have already taught what is extrusion. Extrusion is to get the meat analogues, the texture structure. Remember here in this region the temperature can go up to 180 degrees Celsius and then you will cool it here. So, heating and cooling, that can check the protein structure, protein can be denatured. I have explained all these things already in the previous lecture. During extraction, protein denaturation, protein cross linking happens and that will change the protein 3-dimensional structure and that will change the functionality. So, you will start getting different structures. I will not explain this again because I have already taught you previously. Then there is other technology called cold plasma treatment that can be used to modify proteins. At the interest of time, I will skip that for today, but I am not skipping it from the GAN course. I will teach it in another lecture because it is also relevant in the another lecture. Cold plasma is nothing but it is the plasma, fourth fundamental state of matter, it containing electrons, UV light, everything. Sun is in the plasma state, you know, right, but it is hot plasma. We can generate plasma in cold condition, it is not cold in reality, it is room atmospheric condition. So, then it is called cold plasma, it contains reactive oxygen species, reactive nitrogen species and they will attack the protein, they can modify the proteins, okay, and that will change the functional properties of proteins. It's a new technology, we are also working in my laboratory about cold plasma, how we can use the technology to modify the protein. I will skip this slide simply because at the interest of time, but I am not skipping it from the lecture, I will gonna teach it day after tomorrow most likely, okay. Now, we will move on to the chemical modification. So, we talked about the physical modification, we talked about heating, gamma radiation, UV light radiation, sonication and briefly about cold plasma treatment, but cold plasma will cover later. Now, we will go to the chemical modification, okay. When I say chemical modification, it is not the modification of proteins are chemically modified, it is basically usage of chemical reagents to modify proteins, right. When you use the chemical reagents to modify proteins, then we call it as chemical modification in this context and that will change the chemistry of proteins, in other words, okay. The first one is glycation, also known as the Maillard reaction. How many of you have heard about Maillard reaction? This is something people will always teach if you take food science and technology, right. Any course in food science and technology, they should teach you Maillard reaction. Because Maillard reaction is one of the common reactions happens in food system. It is extremely common. I have some examples, the bread, right. Usually we do not eat bread directly, I mean kids usually use it, you open the packet, you just eat it, but some people like to eat the crust of the bread. It has a different aroma, do you know that? It has a different texture, it has a very different taste. Go to pizza for example, pizza the central portion has a different taste and texture compared to the side one, right. Last day we went to a market here in Rourkela and they gave us a Rourkela special some milk based food. What was that? Channa poda, right? Channa, what is it? Channa pora? Podo? Poda? Podo? So they gave me Channa podo, okay? It's a very traditional Odisha thing or Odia thing. I am sorry, I am poor, I am only good in chemistry, right. So, that was a nice, this was really delicious, right. It was one of the fantastic things to eat for sure when you are in Odisha. Odisha, we call it as Orissa in Karnataka because we do not pronounce D, I mean we are taught Orissa, I do not know why. I know it is Odisha. So, and that Channa poda is basically a dish made up of milk proteins and sugar, right. And it tastes so good and it has a very taste inside and they gave me a crust outside also, it was kind of a black charred one, right. I threw it and she was unhappy and Winny was also unhappy that, why did you throw that, that is the most delicious part. I threw it because I know some chemical reaction happens there. I did not really want to eat that one. So, I will talk about that chemical reaction now, but that is one of the most tastiest part, right? Do you agree? It's a Maillard reaction happening there that gives you that taste, right? And when in the breakfast we don't eat bread, no, you can't eat chana pora without baking, right? You can't eat, right? The taste comes when you cook it. I don't know how they cook it, but I saw they are cooking there, but that's the taste that comes. Bread, when you put it in the toaster, it gets a different taste, right? And now let's take potatoes. This potato I really don't want to eat, but if you give me French fries, that tastes better. Taste is really good, French fries, right? Now I have a chicken, no coffee, the green coffee, not good. Black coffee, nice aroma. Now let's take my favorite chicken. If you boil it, it has one taste. Now if you make a tandoori chicken, it has a different taste. Do you agree? And the tandoori chicken has that crispiness, that redness, mouth watering. But we need to eat plant based, okay? We need to eat plant based. This is only for the diagram, but eat tandoori chicken, it's healthy, don't worry, okay? But what I wanted to say that there is a lot of chemical reaction happening during cooking and roasting that changes the color, flavor, taste, texture, everything, and that is called the Maillard reaction. It's called as the Maillard reaction because Maillard was the French scientist who discovered it back in the days, okay? It has to be pronounced Maillard, not Maillard, because in French it's pronounced as Maillard, okay? You are welcome to call it as Maillard, I don't mind. It's Maillard reaction, okay? And this reaction can be used to modify proteins, okay? Now I'll show you a little bit about the chemistry, what is exactly happening in the Maillard reaction, right? Almost every food contains proteins, not all, almost, right? Almost every food contains sugar, carbohydrates. There are some sugars called reducing sugar, it contains reducing ends. When they come together, okay, protein has an amino group and sugar has this reducing end over here, okay. You are heating them, for example, chana pora, it has milk proteins, it has what they are sugar, sugar, they add sugar. Sugar is glucose and galactose and all, it's sucrose basically sugar, right? And then they are heating it continuously and then they start reacting together and they form Maillard reaction. And the consequence of Maillard reaction is that you get that chana pora crust, that one, and then you get that nice flavor of chana pora, chicken, whatever. It's all because of Maillard. It's a very complicated reaction, one of the most well investigated. Please remember that the reaction happens between sugar and protein or amino acids or peptides, basically amino groups. It looks very simple. Trust me, during Maillard reaction they say 1,000 different kinds of molecules are formed. I am talking about 1,000, maybe more than 1,000, just because of these two reaction. Very complicated, produces numerous reaction and that changes flavor, texture, color of the food, the Maillard reaction, okay. What's that? Can you pass a mic, Asubahir?
So that
Yeah, you see, I can hear you.
Maillard reaction is unhealthy to eat? I mean,
That's a good question, we'll come back to that one, why I did not eat the crust.
Exactly.
I mean, health is another story, I'll come back to that one, okay. I don't say it's unhealthy, okay, I don't say unhealthy, but let's see some of the problems later, okay. So what, I know a little bit chemistry knowledge is required, but I'll quickly go through the mechanism, not in detail. So you have a glucose, for example, sugar contains a reducing end and you have an amino group, for example, protein, which contains an amino group, right. Carbonyl groups are electrophilic, amino groups are nucleophilic and they have a condensation reaction and then you get a Schiff base. That is the first product of Maillard reaction and the Schiff base will rearrange and forms Amadori compound. This is the first stable product of the Maillard reaction. I will teach Maillard reaction for 4 hours back in my university, but I have to teach in 4 minutes now. It's a very complicated, but I'll just tell you what exactly is happening. So it forms Maillard reaction, first is Schiff base and then it forms Amadori compound, but the reaction will not stop here. Basically what exactly happened here is that you have a protein contained amino group and you had a sugar. This was a sugar with the reducing end, right, and they react and now you get a protein connected to a sugar. It is called glycation. Glyco means sugar. Protein glycation means a sugar moiety is attached covalently to a protein. Now, originally it was a normal protein, now you got a protein attached to a sugar. Now, it is a different protein, do you agree? Now, we are doing the chemical modification of protein, that is called Maillard reaction. Okay? But the reaction does not stop here, they further undergo lot of complicated mechanism, they produce volatile compound, they produce highly reactive compounds, and that will change the flavor of the food. For example, this reaction go further and forms a very reactive compound called alpha dicarbonyl compound, C double bond OC, dicarbonyl compound, 2 carbonyl groups, right. For example, one of the famous one is, let us say, glyoxal. It is extremely reactive, and this reacts with another amino compound, for example, amino acid, undergoes Strecker degradation, forms volatile compound. Volatile compound. That is the reason why bread smells so good. That is the reason why tandoori chicken smells so good, because of the Strecker degradation. It forms volatile compound, right. In some cases, this dicarbonyl reacts with protein and forms advanced glycation end product, we call that AGEs. I will show that later. And these advanced glycation end products probably not good for your health. Acrylamide can also form in the same pathway, and she was talking about acrylamide. People say that don't eat French fries a lot because it can have acrylamide. Acrylamide is a well known carcinogen. Now, I am answering your question little bit. Chana powder might not have that one. I don't know. I did not analyze it. Okay, you eat that, and I am not against chana powder. You have to eat. It is your food. Okay, it is dependent how much you eat. Don't eat this much chana powder. It's not good. Small is okay. Is it okay? So, some of the chemical reactions are good. Flavors are really good. Some of the chemical reactions are not good. It can compromise the digestibility. It can form unwanted compounds. It might have a health effect. That is the beauty of Maillard reaction. It is really good. Traditionally used. I am not blaming Maillard reaction. A fantastic reaction to happen. Without Maillard reaction, 90% of food tastes not good according to me. We like roasted cooked food because of the Maillard reaction. Okay. And Maillard,
So, are there any modification techniques like maybe physical or chemical that can control Maillard reaction
Yes.
to reduce acrylamides?
Yes, absolutely. So, you read this paper, okay. You take a photograph of this one, you read this paper. We have, it's actually one of my colleagues, and she has summarized how different methods can be used to reduce unwanted compounds in Maillard reaction pathway. Lot of technologies, as I said, it's my 4 hours lecture, I can't teach now, okay. It can be used. And Maillard reaction also ends up, forms very colored product because it forms melanoidins, and the melanoidins are the responsible for that the crust, and the crust becomes brown, they are all becomes melanoidins, okay, very complicated structures. Okay, now let us forget about Maillard chemistry part, think about they change the structure. Can you see? Maillard reaction, because of the protein sugar interaction, glycation, structure will be changed. When the structure changes, functionality changes. Please note that sugar is usually polar. Now you are adding more and more sugar to the proteins. What happens? Solubility will be changed. So, that is another reason why we are doing the glycation. When the solubility changes, water holding capacity changes, oil holding capacity changes, emulsification changes. So, it is all interlinked with the solubility. So, Maillard can change the functional properties. Sugar can also create hydrogen bonding. So, the protein folding will change. So, that will change the functional properties. So, here is one example, they show the how pea protein concentrated heated with glucose, how it changes the solubility. I do not want you to remember the graphs again and again, just remember that something will change. Okay. And it is a nice summary, they show that they change the bioactivity, it changes the solubility, it changes the emulsification ability when you do the glycation. There is a lot of studies, it is not something new. Okay. And coming back to your own question that you asked, The Maillard gives you dicarbonyl, and dicarbonyl gives you some other intermediates, and the intermediates gives you the aroma compound. It is very nice in some cases. Now, I want to prepare a protein drink, okay, for infant formula. Imagine I want to prepare a protein drink for an infant formula. I am glycating the protein to improve the solubility, right. Now, that infant formula is smelling like a chicken broth. Is it good one? No, right. Please note that Maillard reaction is good, but you have to control it. Otherwise, you will get sometime aroma is good, sometime aroma is not good. It depends upon which product. Chicken should smell chickeny, milk should not smell chickeny. Am I clear? So, you have to be careful when you do Maillard reaction, because it can create some flavor. Flavor is not always good, sometime it is bad. However, you can use Maillard reaction to get meat analogues to have a meaty flavor. That is good, right, because we want to get meaty flavor in meat analog. Maybe you can use Maillard reaction there, but infant formula, no, I do not want to use it. So, depending on the application, it is good and bad. Now, Maillard reaction can also cause sometimes gelation, unwanted aggregation. Keep it in mind. Sometimes it is good, sometimes it is bad. Maillard reaction can also release this advanced glycation end product that I was talking about, and that might have health consequences. There are a lot of research on this. They show that some of the Maillard reaction might be bad. However, it is not completely confirmed. The research in this particular area is like blah blah blah, because they have done a lot of mice studies, but they feed this much amount of advanced glycation end product to mice, and mice will of course get crazy. But in reality, we do not eat this much chanapora, right. We eat only small amount of crust every day, and that might be digested, and we do not care about all these things. But if you continuously eat roasted food, especially if you do fish fries, if you continuously like only the roasted part, every day you eat only the roasted part, it is bad. You forget the other part of chanapora and you only eat crust every day, I am pretty sure it is bad. That is the reason why you have to be careful how much unwanted roasted thing you eat. Am I clear? Because there is a lot amount of glycation in product. They might be bad, but there is no full complete health studies on this one. I have to emphasize this one. There is no health studies to confirm it is really bad. Okay. This is the example here that show how much unwanted compounds forms. CML is an advanced glycation end product. You can see that by doing this glycation, you produce a good amount of unwanted compounds that might have a health consequence. You have any question? Right. And I also do a lot of research on advanced glycation end protein in our laboratory. Our group is kind of famous for this reaction. Okay. One of the biggest challenge here, due to the glycation, we lose the lysine. Lysine is an essential amino acid. During glycation, you basically react mainly with lysine residues. Lysine reacts with sugar. So, most of the plant proteins have less amount of lysine, and now you are modifying them. It is not good. Am I clear? So, you compromise the nutritional value if you heavily modify lysine residue because of glycation. You might get a very nice techno-functional property, but lysines are lost, it might be compromising the nutritional value. It is not always good, they have pros and cons. Okay. About your own question about toxicology, you are welcome to read this one paper that talks a lot about health effects about Maillard reaction end products. Whether it is good or bad, you are welcome to read this paper. Now, we will move on to the another experiment that we do in the laboratory to modify proteins called phosphorylation. Any question about glycation or Maillard reaction? Did you understand? It is good, not always good. That is the take home message. Okay. Now, we will move on to phosphorylation. I need some water. Phosphorylation is a technique we can use to modify proteins. As the word says, it is nothing but adding phosphate groups to the protein. Okay. Basically, you have a protein, right, and the protein contains, let us say, serine residues, and serine residues contains hydroxyl groups. Okay. And if you interact with the phosphate containing molecules, when you interact with phosphate containing molecule, the phosphate can interact with hydroxyl group and you get a phosphorylated protein, something like this one. Can you see this structure? Now, if you look carefully into this mechanism, what did we convert? What happened actually? You had a protein, right, with a hydroxyl group, right. I converted this into a group containing phosphate. What exactly happened? What has actually changed here? Was that?
The hydroxyl group has been
Hydroxyl groups kind of vanished now. Can you see? I don't have hydroxyl group any longer. What has actually new thing you see? New thing?
phosphate addition,
Phosphate. And what is the charge here?
negative,
Can you see?
double.
So, there was no charge here from the hydroxyl group. Now, I am getting more and more negative charge. Basically, you are converting protein into negatively charged component. Again, coming back to my very first class, solubility. No, the fourth lecture, solubility. Solubility is dependent on the charge, right. Now, you are changing the charge of the molecule, that means you are changing the solubility of the molecule, and charge is also related to the pi, right. When equal number of positive and combines with equal number of negative, net charge becomes 0 and protein precipitates. Now, you are changing the charge of the protein, that means you are also changing the pi of the protein. Am I clear? Remember, plant proteins are always having the pi 4 to 5. Now, you are changing the pi of the protein to another level, and that will change the solubility and that will change the functionality. Is it clear? Basically, we are changing the surface charge of the protein by doing phosphorylation, and the surface charge will change the solubility, functional properties. Now, protein is getting more and more negative charge. It can also interact with other molecules indifferently compared to previously when it did not have that much negative charge. So, that will change the functionality. For doing phosphorylation, they use a chemical called sodium trimetaphosphate. It is called as GRAS. I hope I have a point. Yes, GRAS means not the grass. It generally recognized as SUF by FDA. So, you can use it in food in a certain extent. Okay. Instead of that, you can also use phosphorus oxychloride or phosphoric acid to modify the protein. But please note that you are not only modifying serine residues, lysine can also react exactly in the same pathway. Lysine is an essential amino acid, so modification can compromise the nutritional value. Any question about phosphorylation? Here is an example. They show that increasing the content of that what is that called, STMP, the phosphorylating chemical, the rate of phosphorylation is increased. At some point it decreases because you add more and more phosphate compounding group, you change the reaction condition, and that will compromise the phosphorylation. So, basically you can optimize the extent of phosphorylation by controlling the amount of this chemical you use, right. Please note that modification is not something like you need to completely modify protein, you can control it to get the desired charge. And here is an example that shows that you can detect the phosphorylation using FTIR, because when phosphorylation happens, there is a specific IR absorption takes place. So, you can evaluate easily with FTIR. Okay. And this is the paper that clearly shows that phosphorylation is showing negative zeta potential. It means that you get more negative charge on the surface, right. And this also shows that particle size is changing because of the phosphorylation. Protein secondary structure changes because of phosphorylation, it is over here. And this one I have not covered, so ignore it for now, it is XRD. Okay. So, take home message is that phosphorylation changes protein structure and surface charge. Change in the surface charge and the structure changes the functional properties. I hope I have some example. Yeah, example is here. You can see that solubility has been changed with respect to this one. Foaming capacity has been changed after phosphorylation. Apparently, the digestibility from 93 it becomes 95. Significant change, but only a minor change in the digestibility. So, phosphorylation can be used to change the techno-functional properties of proteins. You can read this paper if you want to really interested in emulsification and so on. Now, we will move on to the another technology to change the techno-functional properties called acylation, very similar to phosphorylation. Instead of adding phosphate containing compound, we will add acetylating compound here, right. One of the common chemicals we use is acetic anhydride, this is here. Okay. You incubate protein with acetic anhydride and that will react with amino groups of the protein and you get a new protein with an acyl group here. Can you see? It is called acetylation. So, this new group, can you see it is having a negative charge, right. Originally the amino group was positively charged. You know that the amino groups gets positive charge, right. Now added anhydride, it could be acetic anhydride, it could be succinic anhydride, then you get a group with negative charge. Can you see? Now we convert a positively charged protein into negatively charged protein as a complete modification of protein, and that will change the surface properties, that will change the structure, that will modify the protein. So, you can use two chemicals, acetic anhydride and succinic anhydride. If you use succinic anhydride, we call it as succinylation. Okay. If you use succinic anhydride, we call it as succinylation. If you use acetic anhydride, we call it as acetylation. I have done acetylation. Acetic anhydride is really smells nasty. Don't smell it, it really smells nasty. Okay. It is a good method, but I am not super happy. You need to remove you need to remove all the unreacted compounds, and that is not easy. This looks really nice, but it is not a good method to do in my personal opinion. So, it reacts with lysine. Please note that it can also react with all the hydroxyl compound containing amino acids. For example, it can react with serine, it can react with threonine, it can react with tyrosine, because all of them contains OH group. Okay. So, you are not selectively modifying lysine, you are also modifying other amino acids if you do acylation. Am I clear? So, basically a positive becomes negative if it reacts with the amino group. I hope I have some examples here. This is not required. When you are free, just go through it. How do we do acetylation? Just to showcase again, acetylation will change the protein structure. The secondary structure is dramatically modified when you do acetylation or acylation or succinylation. It is simply because you are adding a big moiety here. A big moiety is around 100 Dalton here. If you do a succinylation, a big moiety is added to the protein, and that will completely change secondary structure of the protein. When the secondary structure of the protein changes, functionality changes. And this is again, they show how the tertiary structure changes when you do succinylation. You do not have to remember the graph, as I said, just remember that things change when you chemically modify proteins, and that can be evaluated by FTIR or fluorescence spectroscopy. I have already taught that you in the previous lecture. And here is a good example that shows that zeta potential, how it is changing. You are getting more and more negative charge on the surface, right, and that indicates that okay, you are changing the protein solubility, you are changing the pi of the protein, you are also changing the particle size, because depending on the charge they interact with each other, or they attract or they repel, and that will change the functional properties. I do not want to teach so much about acetylation, just to let you know that there is a big table in this particular paper. If you read it, they show all the plant proteins, how they have been succinylated or acetylated to change the functional properties. You are welcome to read this paper. So, the take home message is that succinylation can be used to modify proteins to change the surface properties. But one of the important things you have to keep it in mind when you do the chemical modification, you compromise the essential amino acid content. For example, when you do phosphorylation or succinylation, they react with lysine residues, and lysine is an essential amino acid which is already present in a small quantity in plant based foods, and now you are chemically modifying them, you compromise their content. You can see that up to 50% of lysine is lost, and there is a serious loss already present in low quantity, and you are modifying on top of them. Basically you compromise the nutritional quality. Of course, you might get the best solubility in the world, you have to keep it in mind that the essential amino acid is compromised. And I mean, why I want to emphasizing this one, because when you read the research article, they only highlight the positive thing, right, but you have to, as a scientist, should think, am I damaging the protein in a negative way? Yes. Then you find out. It is very important to know in plant based world is that everybody is focusing on the functionality. Oh, I want to get the texture, taste, flavor. There is a less focus on the other unwanted effect. So, you as a scientist, you should think, okay, when I modify, am I damaging the protein in a negative direction? And that has to be kept in mind. I like this very old paper. I mean, I was talking about everybody published the result when you see only the positive result, and this was a paper from 1986, even before I was born, right, and they were trying to modify proteins, especially the rapeseed protein, by succinylation, and they clearly show that turbidity is compromised. It is not actually creating a good gelation properties after doing the succinylation. I read a lot of paper, they show, oh, you do succinylation, you get a better gelation and so on. This the paper shows it does not do a good gelation. And this is the same paper, they also show that foaming properties are compromised. I really enjoyed reading this paper because they openly tell it is not necessarily good, it might be super bad, right. So, always keep in one thing in mind, modification not necessarily change things in a positive direction, it can also compromise negative direction. So, when you become a PhD student, you have to try different modification, and one might work, and that working one might not improve everything, it might decrease something, it might improve something. So, you have to keep in mind that I am not claiming here that the modification will always improve the techno-functional property, they can also have a negative consequences. Okay? And we can also use polyphenols to modify proteins, because when polyphenols attaches to protein, it is a fake polyphenol. Imagine it should be a 6-membered ring, I am showing 5-membered ring here, I am sorry about it. You get more and more hydroxyl group and more hydrogen bonding, more and more polar residue, it can change the solubility, and people are also using nowadays polyphenols to modify proteins, okay, but it will also change the color, just to let you know. Am I clear? So, there is a lot of way to modify techno-functional properties of proteins. So, we will take a break now, right. We covered the chemical modification, for example, succinylation, phosphorylation, glycation, polyphenol addition, many things can be done to modify proteins. They basically change the surface properties of protein, solubility and so on, and that changes the techno-functional property. And next we will see the biological methods. Let's take a break for 10 minutes and then I'll complete the biological modification, let's say in 15 minutes, and then we will take the lunch break. Is it okay? Let's take the break now, 10 minutes break. Yeah. Don't get much time to eat then for you guys. Okay. Okay, are we ready? Okay, welcome back from the break, and we are still on the today's first lecture. So we are heavily delayed, but I'm trying to go things slowly. It's not because I have too many things to say, because too many things are to be modified. Since it's being recorded, I don't want to have incomplete sessions here. We have been discussing about physical methods and chemical methods to modify proteins, and now we move on to so-called biological methods, how we can use different biological things to modify proteins without using chemicals or physical forces. We often think biological methods are natural, right? We have been using historically, and that's the reason why we can use biological techniques to modify proteins. At the end of the day, it's again chemical modification, trust me. We are using biological means to modify, but it's again a chemical modification. That means proteins will be modified chemically by using some biological means. There are two biological means we can use. One is live organism, yeast, bacteria can be used to modify proteins, that we call fermentation. I am not going to teach fermentation today because there will be an exclusive lecture in the future about fermentation, so I do not cover that one. Instead of fermentation, you can also use enzymes. We have already covered a lot of enzymes before, remember? Cellulases, hemicellulases, proteases. We can specifically use proteases to modify proteins because they cleave the protein at the peptide bond region, and that will change the functional properties. We can also use other enzymes, they can use cross-linking the proteins to modify proteins. So, we are going to cover some of these briefly. Since we are running short of time, I am not going to explain detailed things. However, that is not important also, because you already understood how the functionality changes when you just change the structure. So, I do not have to explain that again and again, right. I just show you what do we exactly change here using enzymes, then you think about how that would essentially change the functional properties. Is it okay? The first one is we are going to talk about the most important experiment, the thing we do nowadays is using transglutaminase. It is an enzyme to modify proteins. Transglutaminase is an enzyme that will cross-link two proteins. Basically, it will cross-link glutamine residues with the lysine residues. Now, imagine you have two protein, one with the glutamine and another with the lysine, right. Then if you add an enzyme called transglutaminase, it will cross-link these two residues and you get a new protein where two things are cross-linked. Am I clear? Originally they were individual proteins, now you are combining them covalently by adding an enzyme called transglutaminase. It will transglutaminate, that means it will combine or cross-link or covalent reaction it will induce, that is combination of glutamine and lysine residues. Please note it is a covalent modification, that means it is strong. Now, can you think little bit about why need to we do the cross-linking, what is help, what it will benefit? How cross-linking a protein will benefit you in reality? Niveta?
It will improve the structure, sorry, not the structure, it will texture of the resulting end product.
Exactly, it will improve the texture, because sometimes we need this texture, we need an extra complicated gelation, right, and that can be done with transglutaminase. Am I clear? Please note that transglutaminase also have other chemical properties, it can also do acyl transfer, this is the I just mentioned, it can also do the deamidation, that we will do it later. Just for now, just remember it can cross-link two proteins together. It can also cross-link multiple protein together doing intermolecular transglutamination, intermolecular reaction. When it does an intermolecular cross-linking, then you get a new structure. Multiple proteins can be cross-linked together, they were individually like this one, now they cross-link each other and you get a new structure, intermolecular cross-linking of protein. It is a very important reaction, it gives a fantastic functional properties. Let us take as an example here. These guys were trying to prepare a pea protein based beagle, and you can see that when they increase the content of transglutaminase, the hardness is increasing, right. Now you can see it is very soft here, right. Now they are getting more hard and hard gels, and that has a different functional property. It is very important to get hard gel in many cases. Let us take an example here as a cheese. Now they are creating cheesy structure using transglutaminase. Now on the structure on the left, in the right is without transglutaminase, you can see clearly here, it is more powdery in nature, more brittle in nature. Now if you look into this part here, you can see how nice, how compact it is. Cheese has to be having a cheesy structure, right. You have all eaten cheese, right, paneer for example. If the paneer is very soft and liquidy, do you like it? It has to be hard, and that hardness can be created by creating this protein network, and transglutaminase does that particular job. Am I clear? And you are going to have a last day on exclusive lecture how we can create plant based cheese using transglutaminase. So, I do not cover it in detail today. Is it okay? There will be somebody coming on the last day of the GAN program, that person will talk a lot about how we can use transglutaminase to create a structure. Basically, it will help cross-linking multiple proteins together. It will cross-link glutamine and lysine residues, and that gives you a condensed structure, and that gives you a new texture to the protein. People are using a lot today to create cheese using transglutaminase. Okay? Here is an example that is a real meat sausage. They used transglutaminase. You can look in the texture here. This texture is very different than this texture. It's more soft and more homogeneous, more cross-linked, because the cross-linking is important, because when you tear off meat, and that fibrous structure is very important, and that fibrous structure comes because of protein-protein cross-linking. And here you can clearly see soy protein isolate without cross-linking and with the cross-linking is having more hardness here. Now you can see more clearly here, soy protein concentrate, the fibrous is less compared to here with transglutaminase. So adding transglutaminase actually improving the texture, the fibrous nature of the protein because of this entire cross-linked network. Am I clear? So this is something used in real life in food industries. So there are companies, they sell transglutaminase in bulk, you can use to create new textures. It's a fantastic enzymatic reaction to do if you want a fibrous structure, if you want a gel. Okay? Any question? Okay? And then we have another enzyme called tyrosinase. Transglutaminase will cross-link glutamine and lysine residues. Tyrosinase will cross-link two tyrosine residues. You have a tyrosine. This is tyrosine. Okay? If you add an enzyme called tyrosinase, it will oxidize tyrosine into a compound called a electrophilic compound, something like this one, okay, quinone, right. And when the quinone is formed, basically it can react with a lysine residue like this coming from another protein, then you get a lysine tyrosine cross link, okay, a lysine tyrosine cross, basically now two proteins are cross linked now. In addition to that, in another pathway, it can form two tyrosines can be linked like this, just to give a fake structure, two tyrosines can be linked. This again begins the cross linking, basically. One protein is cross linking with the other protein using tyrosine residues. As I mentioned previously, cross linking will help you get a gelation, right. People are trying to use, now you can see that in this case they are using tyrosinase enzyme here, in oat protein isolate they get a more aggregates here, can you see. So to create aggregates you can use tyrosinase. Aggregation, if you have an extensive aggregation you can get a gelation. Gels are very important to get a cheesy structure, to get a meaty structure. So you can use enzymes to get that structure, am I clear? Then I will take the last one, partial protein hydrolysis. Basically in this case you have a protein, it might have a different property, so it might be having a lower solubility. Now you can use a protease enzyme. There is a lot of commercial proteases are available. You can convert them into polypeptide. Okay. Now the partial protein hydrolysis will help unfolding of the protein. It will reduce the particle size, it will reduce the protein size, and all these things will improve the protein digestibility or functional properties. Am I clear? In the previous case we are actually creating bigger structure. In this case we are breaking the protein to get a small particles, and sometimes they improve the solubility, sometimes they will improve the gelation properties. Why? Because now because of the hydrolysis protein will be unfolded. When the protein unfolds they interact with other proteins nicely and they can create more gelation, more aggregation. So for the partial protein hydrolysis we are using proteases. Any question here? Is basically breaking the protein into smaller pieces. Please note that we use the word partial. That means we are not completely hydrolyzing the protein like we did it in our previous lecture. That is complete hydrolysis. But in this case we do not do complete hydrolysis, we are only partially hydrolyzing the protein. We are talking about 1%, we are talking about 2%, we are talking about 0.1% hydrolysis of protein, not 100% hydrolysis. A small hydrolysis of protein can lead to protein structural change, and that will lead to protein functional change. And I will talk, there is hundreds of different articles about partial protein hydrolysis and improving the gelation, foaming and everything. I do not cover them because I already taught you all these things. I will tell you a little bit beyond that what we can get. Here in this study, they use partial protein hydrolysis. You can see they get the more umami flavor. So, partial protein hydrolysis can be used to improve the flavor properties. Umami flavor is very important to get a meaty structure, meaty flavor. But they are also getting more and bitterness. Can you see here? It is a disadvantage. Why? Because when you hydrolyze proteins, you do protease. When you hydrolyze them, you get a peptides, small peptides. Peptides will have taste. Peptides will have taste. Okay? Some peptides are bitter in taste, that is not good. Some peptides are umami in nature. Some you know about kokumi peptides, there is a lot of research going on. They are dry peptides, basically they give you the meaty texture in your mouth. So, you can use partial hydrolysis to get this meaty flavor in your mouth. But it has to be very balanced. Why? Because when you do a partial hydrolysis, sometimes you get bitterness, sometimes you get kokumi, sometimes you get umami, it is all mixture. If you really want to get one taste, you need to purify them further, it is not easy. Because you have a mixture of 100 different type of peptides, how do you purify them? Again you need to use a purification strategy here. And I think Asta was talking about bioactive peptides in one of the lectures, right? You can also get bioactive peptides using partial hydrolysis. But again, purification is a challenge. You need to purify the bioactive peptides out of 1 million other peptides. It is a challenge, but you can cleave them partially to get the peptides of different properties, anti-inflammatory, antioxidant and what not, and also flavor active peptides. Is it clear? Partial hydrolysis? Any question about partial hydrolysis? Partial hydrolysis is nothing but we use proteases to partially cleave the protein, and that will give you a new functional properties. Foaming, gelation, it is always there. It can also create flavor because peptides will carry flavor properties. Okay? One last thing I will try to cover is deamidation. It is again another enzyme we use, glutaminase. You remember my phosphorylation lecture? You converted some succinylation, for example, you converted positive into negative, right? But there we use chemicals. You can also use enzymes to do this job. For example, if you use an enzyme called glutaminase, it will convert the glutamine into glutamic acid. Okay? And now this was positive, now it becomes negative. So, protein gets more and more negative charge when you use glutaminase. Basically, the surface charge is changed, functionality is changed, solubility is changed. This already I have explained. So, glutaminase can also be used to change the surface charge. So, one example I have shown you here. You can see that by glutamination, you can increase the solubility of the protein. You can reduce the particle size of the protein. Changing the solubility, changing the particle size will change the functional properties of protein. And that brings to the end of my today's lecture, the first one. I will try to summarize quickly. We have tried to modify proteins with different techniques, physical, chemical and biological means. Physical, we talked about UV light, gamma radiation, they are fantastic, they change the functional properties, but they can also damage the protein negatively. Then we came to chemical methods. We use a lot of chemicals to modify the protein. They can make protein positive to negative. We tried about phosphorylation, glycation, Maillard reaction. Remember chicken? Remember chana poda? Remember chana poda? And that's good, but it also has some bad effects. Then we moved on to the polyphenols can also used to modify proteins. Then we moved on to the biological methods, fermentation and enzymatic. Fermentation I will cover in the next lecture. Enzymatic, we can use many enzymes. One is transglutaminase, fantastic enzyme, cross links the protein, you can get cheese, you can get meat analogs. Then we discussed about tyrosinase, it can also cross link the proteins. It is not well investigated in food system, just to let you know. Then we talked about partial hydrolysis, partially cleave the protein 1%, less than 1% usually, that will change the protein structure. However, the beauty here is that they can also release bioactive peptides, they can also release flavors. And the last one we talked about glutaminase treatment, it will convert positive into negative charge, and that will change the solubility, protein-protein interaction, it can change the functional properties. And that brings to the end of the first lecture of today, and we will have the second lecture in the afternoon. We will come back at 2:15, we will talk. Hello everyone and welcome back to the Gian program again. So, the next generation sustainable alternative proteins for food, fundamentals and technological applications, and in the first session we discussed about what did you discuss in the last session? Exactly. In the last session we discussed about how can we modify proteins to improve or to get the desired techno-functional properties. We discussed about physical, chemical, biological and so on, and now we are going to little bit slightly different topic, I would say, that is lecture number 13, scaling up production from lab to commercial scale. Okay. I must tell one important thing here is that we are producing alternative proteins for the consumers, right, especially human beings. I mentioned to you that the population of the globe is increasing, and we are going to be about 9 or 10 billion, something like that by 2050. So, we need to produce several fold higher food that we are producing today. I have already covered that in my very first lecture, right. We need to produce more food means we need to produce more protein. We also discussed a lot about quantity versus quality, right. Quality is very important, essential amino acids are important, digestibility is important, but quantity is also important because we need to feed more and more people. So, that means that we need to produce more alternative proteins, and we need to extract more alternative proteins, and sometimes we may have to purify alternative proteins to get the desired benefit, right. When we talk about human being population around let us say 9 billion, if you really want to have a transition from animal based to plant based or alternatives, then we need to produce them in a large quantity, and we need to purify them also in the large quantity. Large means really large I am talking about. Okay. Now, I am going to talk little bit about different purification technologies and why we need to purify them. I must also admit one thing that I am going to take this session, this particular lecture as a freestyle lecture. That means I do not show you a lot of slides now. It is simply because I could not find really nice research articles, especially in the alternative protein area, how they are using large scale purification technologies. I could not find anything, but there is a lot of thing has been done in the milk based area, how they are purifying dairy proteins. In principle, they same or similar technology being applied to alternative protein world, but I do not have a strong evidence to show some good slides for you. I will take it as a freestyle, and I am going to talk little bit about why we have to purify, what we are purifying and how we can purify. Is it clear? The first question is why we need to purify proteins. What do you think about? What do you mean by purification of proteins? Because we talk about many different words. We talked about extraction of proteins, we talked about fractionation of proteins, now I am talking about purification of proteins. Are they similar or somewhat similar? Any answer? What do you mean by purification of protein? You have a mic, you should talk now. What do you mean by purification of proteins? Yeah.
Purification, we need to remove these anti-nutrients or other impurities.
Exactly. So, we know that anti-nutrients and impurities are the big problems because they compromise the digestibility, right. Even they are present in a very small amount, they can compromise many things. For example, we were discussing about the problems with polyphenol. Remember that color we got? Even the polyphenol content is less than 1%, the protein becomes super colored, and we do not want that color. So, we need to further purify proteins. So, any other reason we have to purify proteins? Any other reason why do we have to purify proteins? All right, I give one example now. Okay, why do we have to purify proteins? Let me take an example of rapeseed, that is the protein we have been working today, at least in our laboratories. Rapeseed is a seed, it is an oil containing seed, right. And after getting oil out of the rapeseed, we get a press cake. This is called cake. Okay, we call it as press cake, and the protein content in this press cake can be, let us say, about 35%, right. And then I use different extraction technology. We discussed about lot of extraction technology, right. Imagine I used ultrasound or whatever extraction technology, or imagine I try to do air classification after removing complete oil or something, I did something, right. Now I can get two kinds of main fractions, what we call rapeseed protein concentrate and rapeseed protein isolates. By doing different kind of extraction, I can get these two things, right. And usually you have heard about soy protein concentrate, pea protein isolate, and I already mentioned to you guys what do you mean by isolate and concentrate. In general, we believe that if the protein content is above 90%, we call it as isolate. There is no strict rule for this one. If it is above 70%, we call it as concentrate. Otherwise, we have flour. For example, pea flour, other flours, they have around 40% ish protein content, right. Now, I got back to you another point that we have been discussing. Plant proteins are never alone. Even if I say 90% purity of rapeseed protein isolate, it is not a single rapeseed protein that is present in this 90%, right. It is not an individual protein, it is a mixture of different proteins, right. I have gotten it 95% pure, but it is not the 95% pure of individual protein. Does that make sense? Rapeseed contains two types of protein, let us say nepin and cruciferin. Okay. It contains two types of protein, nepin and cruciferin, right. We discussed about nepin has a melting point or denaturation temperature about 100 degrees Celsius, and cruciferin has around 80 degrees Celsius. Let us take that into consideration. Now, if I want to use this rapeseed protein isolate in food products, since they have a difference in their melting behavior or the denaturation temperature, I might get different properties in the food samples, right, because they are dissimilar. One is an albumin protein, other one is a globulin protein. For example, cruciferin is a globulin, nepin is an albumin. Now, we have a mixture of albumins and globulins together, they have a dissimilar properties. Perhaps I might get a techno-functional property that is something different than what I was anticipating. Make sense? Now, since they have different properties, now I will start using purification technologies, right. Somehow I can take a nepin fraction out, and somehow I will take a cruciferin fractions out. This is different than extraction. Can you see? We started with extracting, we get a protein isolate, but the isolate is not necessarily an individual protein, it is a group of so many proteins, and if they are having a different properties, you might compromise functional properties. You might have a good properties, but sometimes we need a different kind of functional properties, then we need to sub-purify the rapeseed protein isolate, right. And please note that when I say nepin, again it is not a single nepin, it has its own nepin classes, nepin 1, nepin 2 and so on. Cruciferin also has its own isoforms, so and so. So, you can further purify them if you want, then you get another fractions here, right? Right, and these will have a different properties perhaps, and that means we started with the crude sample, we extracted something, and then we thought we purified, we got something. No, it's not the end of the story. You are again purifying to get a different things, and that is the concept of purification. Does that make sense? Why we need to purify and how we are purifying today? Is it clear? To get individual, I do not say maybe now I have maybe 90% nepin. This 90% nepin is not equivalent to this 90% rapeseed protein isolate. Do you agree? And here I am getting like 99% cruciferin after purification. Example, I am just giving a fake example. This 99% cruciferin has a different functional property than this 90% rapeseed protein isolate. So, and that is the reason why sometime purification becomes super important to get an individual protein out for a dedicated functional property or dedicated food applications, right. And one thing I must tell you that every purification step you introduce in a process, you lose a protein, a fraction of protein is continuously lost. Often purity and yield are inversely proportional, right. If you want high yield, you have to compromise with the purity. If you want high purity, you need to compromise with the yield. They are inversely proportional, and often, I do not say every time, but often they are, because every single processing step you are introducing, you lose some part of what you are trying to purify. That is the problem. Process efficiency is never 100%. Okay, of course, we have to optimize it. That is what the whole research in the protein purification world. Am I clear? Why are we purifying and what is the bottleneck here? And plus, every time you purify, you need to spend time and you need to spend money. So, when you increase the purity, the cost of the sample, the product can also increase dramatically. Make sense? When you increase the purity, you might get a good techno-functional property, you might not get also as well. However, every step you are introducing, you lose protein, or also product is becoming more and more expensive. That has to be one thing we have to taken into account when you say purity. Clear? Any question about why we are purifying? Is it clear, right? Now, we will talk little bit about how we are purifying today, right? So, let me go to, now you have to help me with this slide actually. Which protein shall we take? Let us take again rapeseed only, because I like that, because I am working a lot with that protein. Okay. Now, I have a rapeseed, this is seed, right. My end product, I want nepin, okay, and I want cruciferin. This is my expectation. Okay. I would like to have 100% nepin and 100% cruciferin, that is my expectation, right. Now, you should explain me how we can purify these two individual sets of proteins from seed. What would be the steps? I have taught you a lot about extraction already, so many things I have taught. What will be my first step? What's that? Dehulling, right. The first step he is telling that you go for dehulling. Now, somebody has to explain me what actually you remove by dehulling. The outer seed coat, and that contains tannins, polyphenols and all these unwanted things we do not want to eat. Usually seed coat is not so good to eat, they are bitter, though we just want to discard them, right. How do we do dehulling? Mechanical processes are there, you are chemical engineers or mechanical engineers, you know better than me. So, dehulling, there are machines to do the dehulling, let us say. After dehulling, what will we do? Defatting or de-oiling, right? Defatting or de-oiling. Yeah, exactly. They missed one step. We can't do the de-oiling directly on the whole seed. What will we do? Milling. That is why I need help, okay. We need to milling. What do you get after milling? What is the product? you get fine powder. Okay. Once you have the fine powder, what is the next step? Defatting, right? The next step is defatting. Can somebody explain how it's being defatted today? Yes, you can use hexane. That's what industrially being used. It's allowed as long as you remove all hexane from the sample in the oil press. Anything else? Cold press or hot press. We use both cold pressing or hot pressing. It's basically pressing under a screw. Okay, oil is removed. And what do we get here at the end of the day? Oil and cake you will get. Oil and cake we will get. It's not that cake, okay, it's rapeseed cake. Oil we don't want for now, that is the business of oil industry, and they will take it and they will sell it, they will make money, that's not my problem. We are protein guys now, okay. Now we have the cake. Oil is actually ready to use, but cake is not ready to use. It's only ready to use for animals. We are animals, but we can't eat cake. This cake, make sense? Okay. Now defatting finished and I got cake. What do I do next? What do I do? Extraction. Now I will go with extraction. Next step is extraction of cake. Okay. Tell me about some extraction. What extraction will you use? Okay, the most commonly used is alkali extraction, I have told you. So, I take the press cake, now it is actually pressed, so it looks like a cake. I do not want to add alkali solution directly to that one. What I will do? I will again mill it, right, I will again homogenize it. So, milling or homogenization. Okay, next what will I do? I will add alkali, right. I will add let us say a sodium hydroxide solution containing pH 9, or I will first add water and adjust the pH, whatever I will do. So, I will add alkali extraction. Okay. Basically, I have a big jar containing rapeseed press cake and added with sodium hydroxide, right. Next what will I do? Centrifugation or fractionation. The most common, the easiest thing is to do the centrifugation, but large scale centrifugation is also expensive, right. People use muslin cloth or cheese cloth, many things that people use to reduce the cost, right. Let us take it as a centrifugation, because you need to separate the two fractions now. I just write it as centrifugation. Centrifugation, okay. What do I get? So, I get two fractions from the centrifugation. I will come on the left hand side, you can see, right. Okay. You get supernatant and pellet. Supernatant and I get pellet, right. What will be there in the supernatant? So, I will have protein, P for protein. I will have polyphenols, PP for polyphenols. What else? What's that? Carbohydrates, I will have some carbohydrates also here, right. Then anti-nutrient factors, A and Fs, then what else? What's that? Sodium. I might have lot of salt, it is coming from sodium hydroxide, and also the seeds also has salt, in the sense they have minerals, like they have calcium, magnesium and everything. So, I will have minerals. Shall I write minerals? All right. What do we have it in the pellet? Mainly insoluble fibers, right, because they are not soluble in sodium hydroxide, let us say, they are insoluble fibers, that is the main composition. Anything else will be there? Still there will be some proteins will be there, do you agree? But a minor content. Only the alkali soluble fraction will come to supernatant. Please note that we are also already losing some protein. First step, we already lost some proteins, a lot basically, right. Usually we do not care about pellet, because although some protein is present, it is very dirty, you will throw it or use it for fiber preparation, some other application, right. There's a lot you have to discard also here. It's not a very circular economy bioprocessing. We can do it, but that's another story. Okay, now supernatant has a lot of protein. What will you do? What will you do? Precipitation. Which precipitation? Isoelectric precipitation. So I will do isoelectric precipitation. What will I add? I will add HCl to adjust the pH to Pi. How many fractions I will get? So I will get a solution here. It looks like this. I will have supernatant and pellet, right? I will have supernatant and pellet. Supernatant and pellet. Okay, what do we have in the supernatant? What will we have in the supernatant? Again some proteins only, right? Mainly albumins. Okay, we will have proteins. It also globulins will also come. So we have proteins mainly. Do we have some antinutrients here? Yes. Do we have some minerals and metals and everything here? Yes. Do we have polyphenols here? Yes, because they are all soluble, right? So we still have a lot of thing accumulated. Now the pellet, what do we have? Small amount carbohydrates you removed a lot here, but still some carbohydrates are left here, right? What do we have left? Still you have a lot of proteins here, because those are the proteins majorly globulins, they are precipitated, okay? Globulins are precipitated, so you will have protein mainly globulins, simply because you remember that our PI diagram, all the globulins precipitates at 4 to 5. It is also true for this one. Now, which one is the globulin in rapeseed? Cruciferin. So basically you will have more cruciferin here. Will you have a nepin here? You might have, but it is very unlikely to have nepin. Why? Because nepin has a long solubility, it does not precipitate. What about this one? Which type of protein you will have? The supernatant? Majorly nepin you will have, okay? And small amount of cruciferin might be also present, because some fraction is soluble, it is not precipitate everything. So you have still cruciferin. The major is nepin, less is cruciferin, here major is cruciferin. So now can you see how you nicely separated two proteins already? You are becoming more and more clever now. Is it the end of the story? Still we have to do a lot, right? Okay, now I need more of proteins now. I have the two possibilities, either I can take supernatant or I can take pellet. Of course, in between there is a centrifugation is there, I did not write. So I have supernatant, I will have a pellet. In reality, we will take both of them, but we will process them separately, okay? Now let us go with the pellet, because pellet usually have high amount of protein. Is it okay? You can also work with supernatant, but I will go with the pellet. Pellet has a lot amount of proteins. What will you do? Was that? Okay, so she is telling that she wants to get rid of many things. For example, the pellet will also have small amount of carbohydrates, but small amount of anti-nutrition factor compared to this fraction. Do you agree? Because anti-nutrition factor could be more soluble, so they try to go to supernatant, right? Polyphenols are more soluble, so they try to go to supernatant. Pellet will have them, but in a small quantity compared to supernatant. That is the reason why I am going with pellet now. You are welcome to take supernatant to make your life little bit difficult, but I will go with pellet to bring with. Now, it also has a small amount of polyphenol, minerals and everything will be there, because they actually bind to the protein. So, when protein precipitates, they will also precipitate, that is the problem, right. So, now we have pellet, and she is telling you will go for membrane filtration or dialysis. Dialysis? So, she will go for membrane filtration, we call it as membrane filtration. What do you get? No, okay, when you do, I'll get back to that one. When you do membrane filtration, we will get two things, a retentate and a permeate, right. This is a membrane, right. and you add your protein solution to this one, you will get permeate and retentate. The membrane is basically a molecular cutoff, just you cut off based on the particle size, right? That is the membrane. Depending on that, you will cut off. What do you usually get in the permeate? Yes, exactly. So, we will have permeate and retentate, and he is telling that in permeate you will have polyphenol, minerals maybe, and retentate protein. Depending on the molecular weight, the pore size of this membrane, you might get protein. Do you get some proteins here? Exactly, some low kilodalton ones that can pass through the holes, pores can also come here, right. Now, this can be further purified because you still have protein, minerals and polyphenol. I want to get proteins out of it. What shall I do? What's that? You can do size exclusion chromatography, right, put it on a column, then I first get protein or I first get minerals? Size exclusion chromatography, the bigger one comes first. So, I will first get protein fraction and then I will get fraction number 2, I will get minerals, polyphenols or something. Now, I am getting kind of a very, very pure protein. Am I clear? The same thing can be done in this direction also with the retentate, same phenomenon. Am I clear? I get some proteins and I will get rid of minerals. Look, can you look into this, can just take a look into this system what we are doing now. It is not something new I am telling, people, everybody is doing the same thing. So, how many steps we have to get a purity, let us say 80% or 90% or something like that? How many steps can you can count here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There is 100 different steps we can, because you have to prepare other things also in meanwhile. It is not an easy essay, I write it in a box here, but there is so many processing steps involved to get the protein. Originally protein was in the seed, now I have a protein in my hand. Okay. In between I used air classification, drying and sorry, drying is not done yet. So, I still have a liquid fraction here and then I will dry, then I will get the powder and that powder might have 95% protein, might have, I have no idea. Make sense? So, this is the processing we are using today to get alternative proteins in a very, very pure form. In between they modify too many things depending on the situation. For example, you do not have to do isoelectric point precipitation. Okay. Where do we do isoelectric point precipitation in this diagram? I am so much confused now. Which step is isoelectric point? Here, right? This one? Right, I did not write isoelectric. Here, exactly. Here we are doing, sorry, here we are doing isoelectric precipitation. Once you do isoelectric precipitation, you get a pellet and supernatant. What you are telling that then we can do membrane filtration, but you do not have to do there. When you have a supernatant and pellet here, the supernatant this here, this can directly go to membrane filtration. You can do that without any problem, depending on the situation, of course. So, they will try to modify depending on the situation of what you want to extract. Now, the take home message is purification is not an easy task, right. You can ask me one quick question, why can't you do immediately size exclusion chromatography from the scratch? Can you do a size exclusion chromatography here? No, it becomes super complicated. What we are doing, we are trying to sub-fractionize protein slowly. Every step you remove something in this side or this side, right. Every step you remove something, at the end of the day you get a fraction rich in protein. It is not 100% protein again. Again it is a mixture of proteins. Again you have to do another kind of purification. So, it is not a thing that ends, in my opinion. So, you can do again purification, you can do again do many things depending on what do you want. Any question here? Looks good? When you go home, you will make this assignment. Just close your eyes, take the protein you want to work with in the future, maybe housefly, maybe cockroach, maybe microalgae, I have no idea. Hold it in the hand, not the cockroach. Think about, hold it in the hand. And now think about, how do I get a protein out of that particular biomass, and try to make this flow chart. It is really fun. It's really a good exercise to do at the end of this particular course, because this actually it covers too many things. Once I have powder, then I know all these problems: digestibility problem, techno-functionality problem, water holding capacity problem, all this problem you have here once you get the protein. Am I clear? And depending on the purity, where do you get the protein? Depending on that, you will have different techno-functional properties. Now, yes.
Sir, out of curiosity, I'm asking. So, whenever we do it in industry, it is a very huge biomass that is converted
Yes.
to get the protein.
Yes.
So, is there that much big size exclusion chromatography
Yes.
to purify?
Good question. Size exclusion chromatography can be scalable, but the biggest problem is that you can't scale to that level you are expecting. It's
Yes.
because, again, in the normal size exclusion chromatography separates by gravity. So, basically you need to pour, wait and forever. Of course, you can apply some pressure or something like that. It's not very efficient process. However, the membrane filtration is a very efficient process. You don't have to do size exclusion chromatography here. You can do ultrafiltration.
Yes.
And that is efficient, that is scalable, that is continuous. At the moment, people are using
Ultrafiltration.
ultrafiltration or microfiltration, reverse osmosis, electrodialysis, so many other things, because they are all kind of continuous and scalable.
Thank
That's a
you.
good question. I'll come back to that again. So, size exclusion chromatography is not necessarily a, it's scalable. I'm telling you, it's not unscalable. It's scalable, but may not be that efficient compared to other processes. Maybe I'm not an expert in pilot scale production. I must admit that one also, but I work with people, so I understand. Okay. Any other question? You'll make this homework, right? Great. Now, she asked the question about size exclusion chromatography, is it scalable or not. Usually, you can work with many things, but we try to use in industry a process that can be made continuous. We do not want to use a batch processing method. We do not want to use something has to be cleaned again and again. We want to have things that is continuous, because continuous saves money and time, right. And now you have a final fraction, imagine, that contains let us say protein 1, protein 2, protein 3, P1, P2 and P3, and we also have polyphenol, we also have some anti-nutritional factor, and we also have some minerals left. Okay? Am I clear? Now, I have a final fraction. It has protein number 1, protein number 2, protein number 3. It also has some polyphenols. It also has some anti-nutritional factor. It also has some minerals. Now, if you look into the composition of the final fraction I have, they have different molecular weight. Can you see? They have a different molecular weight. What does it mean? Their size is also different, in other words, right? Protein 1 may be bigger than protein 2, protein 3 may be bigger than protein 1. Polyphenols are small compared to protein, right? Polyphenol molecular weight, let us say 300 Dalton. Tannin molecular weight, let us say 1000 Dalton. Protein can be 15,000 Dalton, 300,000 Dalton, so big, right? And then anti-nutritional factors, sometimes they are big, sometimes they are small, depending on whether it is a trypsin inhibitor or whether it is a lecithin. Depending on that, we have a different size. Minerals, very small, tiny, right? Do you agree? Now, what I am going to tell you is that we have different sizes in the system, right? Big one, relatively small one, the smallest one, and depending on the size, we can use different purification technique, filtration technique, right. I found this one is in a very nice article. Depending on the size, what kind of methods can be used to purify. Am I clear? You can see the size of the particle here, can you see? And the technology here. Proteins are in nanometer size, right, very small. If it is aggregates, they become micrometer size. Bacteria is in micrometer size, right? Bacteria is in micrometer size, microalgae is also micrometer size, cell wall may be in micrometer size, fibers may be in micrometer size, you are centimeter size, right? I am talking about the size relativity. So, based on the size we can separate people and things, right. Now if you want to do microfiltration, basically they have a size, you can see over here, okay. If you want to have a size ultrafiltration, they separate from, let us say 10 to 20,000 or 10,000 they are telling. I think usually it is 1,000 to 200,000 according to the literature. So, you can use that one, ultrafiltration. You can use electrodialysis especially to separate minerals, right. You can use ion exchange chromatography to separate proteins with different charges. If you have a bigger particle, very big particle, you can use centrifugation, that is what we did here, right. Because the density is different, by centrifugation you can separate them. You can't separate soluble proteins by centrifugation unless you centrifuge it in next level. Maximum use 20,000 G, let us say. Can you separate soluble proteins 20,000 G? No, only insolubles will be precipitated, right. So, you can use centrifugation if you have a bigger particle. So, we are using all these things to get the final product. For example, if your matrix have bigger particles, first you centrifuge it, okay, then you get this much. Then you do microfiltration, you remove some of the portions. Then you do ultrafiltration, you remove some of them. Then you do nanofiltration, you remove some of them. Then you do reverse osmosis, you remove the final minerals. So, it is basically step by step you are doing to get the final so called ultra pure proteins using membrane filtration. Often people not use all this combination, they use 2 or 3 to get the best ones. Am I clear? So, this is the diagram which clearly shows which kind of filtration you can use to get the particles, right. To membrane filtration operates at 1 to 3.1 to 3 bar, it is the flux, the pressure they need to pump to the membrane. Membrane filtration is nothing but a membrane is here. To make it very simplistic way, sorry, it does not look like this one. So, this is called feed. Feed is nothing but your sample, right, you feed it. And then there is a membrane, they are semi permeable, permeable, there are different kind of membranes are available. Membranes will have a hole or pores, right. Depending on the pore size, we call it as microfiltration, ultrafiltration, nanofiltration, reverse osmosis and so on thing. So, you continuously supply your sample to this one and you collect the fraction. Am I clear? So, the one it is coming here, it is called retentate, the one here is called permeate, okay. Depending on the type of membrane, so we have membrane ultrafiltration, microfiltration and so on, right. Now, if you want to get only a micro particle from your protein, which filtration will you use? Microfiltration. Microparticles will be maybe cells, maybe protein bodies, maybe big chlorophyll, they are all micro, can be gone, big particles, right. If you want to separate proteins and something else, then you have to go for ultrafiltration because proteins fall in the ultrafiltration range. If you want to separate minerals, osmosis, reverse osmosis you can use, of course, I do not think there is an electrodialysis here, electrodialysis can be used. Am I clear? So, depending on the need, you need to use different kind of things. Please note that when you do salt extraction, for example, when you do alkali extraction, you have to remove the salt. You can't do freeze drying because salt will be accumulating, that is not good for the health. So, we need to do one sort of filtration, it is very common. This is how the filtration system look like, just to give an idea. So, the feed is continuously coming, I do not explain all these things, I am not a mechanical engineering, and this is the membrane what we have. So, here you get the fractions retentate and permeate. Am I clear? And there is something also called diafiltration, have you heard about it? Diafiltration. In ultrafiltration what we do, we have an ultrafiltration membrane. Ultrafiltration membranes are very fine membranes, they have a molecular cutoff of let us say 10 to 50 kilodalton. Okay, this is ultrafiltration membranes. Basically, proteins can not pass through depending on their molecular weight, cut off here, and some proteins will come here and some proteins will come here. For example, if I use 10 kilodalton membrane, what will happen? Anything more than 10 will be in the top, retentate. Anything less than 10 will be in the permeate. Minerals will also come in the permeate, do you agree? Because they are smaller than the proteins. So, you have to do again maybe dialysis again of that sample, right. And this is called ultrafiltration. In case of ultrafiltration, they can always combine with diafiltration. That means, you can continuously add more and more solvent to the system to clean it again and again and again. Then the process becomes diafiltration. Am I clear? Ultrafiltration is often coupled with diafiltration to clean it further, to purify them further. Now, this is the process. Now, I talked about different steps. I talked about membrane filtration, that is scalable today. What are the problems you think with respect to membrane filtration for large scale protein purification? Fouling of the membrane is one of the biggest challenges the whole membrane world is facing, because I say they are tiny pores. We are supplying protein with big different sizes and they can block the pores, they can make a thin layer on the membrane, right. They can adsorb on the surface of the membrane will foul, no longer allow solution to pass through. Then you have to apply more and more pressure to remove that one, then the membrane can rupture, right. Process efficiency can be severely compromised if the membrane is fouled. Fouling of the membrane is a problem. To avoid that, there is a lot of research is going on. They are using ceramic membrane nowadays, they are using membrane that is not reacting it with something else. There is a lot of chemistry, physics, mechanical engineering is going on in this field. It is also a nice field to go do research. Am I clear? Dairy industries is using it a lot means a lot today, membrane filtration to get whey proteins, for example. Am I clear? I do not go deeper into the membrane filtration, that is not my area of expertise, but this is how we are using. Is it clear? Any other disadvantage? Cost. Basically, the membranes are expensive. If they are fouling again and again, you have to remove it. If they do not foul, for example, you can reuse them. Continuously you can reuse them. It is only a capital investment, then no problem. Am I clear? But that is not in reality. Any doubt about membrane filtration? Is it clear? Membrane filtration is nothing but a filtration used based on membrane. Depending on the type of membrane, we have microfiltration, ultrafiltration, nanofiltration, reverse osmosis. Each of them will pass through one type of molecule depending on the size, and that can be exploited to purify proteins from small molecules. Okay? Ultrafiltration is often used combined with diafiltration today. Apart from membrane filtration, people also use adsorption chromatography. We have a company in Denmark, I found it is from their website, and they are trying to use kind of, you can find this in the YouTube video. If you go to this website, they have a nice YouTube video how they are using. Instead of using membrane, they use an adsorption stuffs basically. Proteins have affinity for ligands, right. They bind to some kind of, I do not know what they are using here though, they bind to, they say they bind to this kind of particles here, and they see when they selectively bind to the particles, you can purify proteins. Okay? Basically, I think I taught you this affinity chromatography earlier, right? You have particle, okay, and you have protein. If this particle likes protein, it will bind, right? The rest everything will go away. Then you would an elution buffer to remove proteins away. Okay? So, these kind of technology can also be used for large scale purification of proteins. Am I clear? Often membrane filtration is used, but I found this company they are also using other kind of technologies to purify. Please note that certain things are very scalable. I would found it from their internet on their website that they say they can manufacture, or this can be scalable to very large scale, something like that. So, there are big equipment to purify protein. For example, to purify dairy proteins, we are talking about the the plant, it could be like of whole building size. So, it can be made very scalable. All right, that is all about large scale purification. We get an extract, we are not happy, we want to get an ultra pure protein. If you want to get an ultra pure protein, you have to use different technologies. Often used is membrane filtration, and that gives you a highest yield, highest purity. I don't know about yield. It varies from process to process, protein to protein, and there is no evidence. People are using, I know, but in the internet I could not find a lot of articles on how alternative proteins are being purified today. There is a lot of article on milk, but alternative protein there is a less article, because some of these technologies are patented and they do not want to tell you what they are doing. So, that is a problem. So, we do not have a scientific research. Any question? That concludes my last lecture of today, large scale purification of proteins. Thank you. Any question? Yes. So, we take a break now. So, because we are done with today's class, and we will have, after the break, we will have a session tutorial. We will start with the tutorial. I suggest we take 15 minutes break, and then we will gather again here.